Oh, okay. That's all right. Having flashes of COVID. All right, good to go from back to your side? All right. All right, welcome everybody. I'm Charles Herring, Chief Technology Officer and co-founder at WIDFU. We're going to talk about building a global cyber grid, sharing data across clusters on Cassandra. Up on, I'm going to get off the stage for a second so I can see my own screen. But up on the site, we have charlesherring.com. This is my personal blog. We have this talk, some other talks I'll reference are also up there. My social media things, if you'd like to connect, please do. We can continue the conversation. So a little bit on the agenda, we're going to cover sort of the scope of the project that we're working on, how do we distribute configuration across clusters, the idea or theories of predestination of data, how do we configure key spaces, dealing with natural language processing, graph processing, and federating data ops. So a little bit about the scope of what we do in the WIDFU project. It's taking in tons of data from different organizations, different users, customers, storing it, processing it for a wide array of different personas. So your standard security operations center folks, so the guys that are knocking bad guys off the network, stopping, responding to incident response. Auditors that are doing audits for compliance, regulatory, legal issues, insurers, law enforcement, so reporting crime, investigating crime, dealing with national security. So it's about bringing everybody together and utilizing data, sharing intelligence in a way that can drive down cybercrime. So we're talking about hundreds of organizations that are bringing in hundreds of gigs or 10 or more terabytes of data each day. The data may have to be stored for years, so you're talking about a lot of data stored, a lot of data in motion, and we want to coordinate some of that data, if not all of that data, across multiple clusters. So from an input-output perspective, in each cluster, we're looking at different data sources coming in, so syslog messages from servers, from different applications, networking data coming from the network infrastructure. This also includes flow logs from AWS VPC, so any communication, any record of metadata of conversations, agents on different endpoints, shipping that data in, and then connecting to hundreds of different APIs and pulling that data into each cluster. The clusters communicate in an upstream or a downstream capability. So if the cluster wants to push data to another cluster, it can. If it wants to pull data from another cluster, it can. We'll talk about how we do that along the way. So inside of each cluster, there are different components that are responsible for different parts of the processing. So we have data ingestion that's going into a Kafka topic. And so that's just a raw message. So we have transport of different types, writing to a topic. The contents of that topic are subscribed or consumed by a natural language processor that's analyzing those raw messages to comprehend what does that signal mean, where did it come from, what are we supposed to do from it, what product created it, how do we parse it, and then that's put into a separate topic. That data is then consumed by a graph processor to understand the relationships that are inferred from the signals that are being received. Then we're going to analyze on a different topic what we're learning from that graph. And we're going to create units of work, reporting, different types of analytics Those will go into Kafka, and those will be written as different streams into Cassandra. With 5.0 coming out, we're working on vectorizing or using vectors in that data for prepping for generative AI and other LLM. So another issue that we sort of have is it deploys everywhere, right? So we have some that are deployed on Raspberry Pi, some that are deployed in multi-cloud, multi-data centers. So each node can deploy however it needs to be deployed. So whether that's a piece of physical hardware in some place, inside of a public cloud, private cloud, across data centers. So each node can be configured on whatever fabric it needs to be deployed upon. So handling that, how do you connect different data nodes, processing nodes, Kafka nodes in a cluster that are potentially geographically dispersed, different network topologies. So to do that, we use an agent, a daemon, that receives an input from either a user that's manually spinning up a new node or an orchestration script that tells us where it is, so what data center are we in, what rack are we on. The license key, which helps identify what customer organization, what user cluster is this thing a part of, and what role should we spin up? Is it just going to be a new data node, or are we going to do Kafka? What is its role going to be? Then the agent uses that data, goes to a consolidated service, which we call library or WITFU library, and says, give me the basic information I need to join this cluster. And so it comes back with the seed nodes that it might need from Cassandra. We use some brokering for shared secrets so that it can join the cluster. And so it has the secret, it has the configuration, and then the agent pulls the Docker images that it needs. So if it's Cassandra, it'll pull a configured Docker image of Cassandra and spin up that container, or if it's Kafka, or if it's one of our NLP agents, whatever needs to be configured, it does. Launches that container, it joins the cluster, and then it ships metrics up the library. On my website, I do have another talk called Metric-Driven DevOps. It sort of goes deeper into how all this coordination happens and how we ship metrics. Feel free to grab that. You don't even need to give me an email address. And then all those issues, alerts, metrics boil up to library. They come to the WITFU support personnel. They go to the cluster. They go to the end user and customer. So this idea of predestination of data is how I describe the overall philosophy for processing multi-cluster data for many types of persona. So in data in particular, or data broadly, and cybersecurity in particular, we've taken a philosophy of putting all of the data into data lakes, and with the idea that we're going to figure out the questions later. We'll re-index the data, we'll figure out what we're going to do with it. But this philosophy that we leaned into is when we receive a signal, we need to know everything that's going to happen in the life cycle of this piece of information. How will it be transformed into new information? Who will query it? How long will it live? So giving it a time to live when it dies. And so understanding sort of everything that could possibly happen in the entire life cycle of this piece of information is critical to how we handle information, which means we're constantly having to interview the different personas, looking at different end games of the evolution of that data. So in building out the schema, or the tables in the key space, so the key space configuration, we tend to start with a simple replication strategy on replication factor 3, but when we have things like multi-data center, and so network topology, we can move that as it needs to be done. But the key part here is how we construct tables. So the partition key, and I'm going to walk over here for a second, but the partition key is, are you on? You are on. Laser. Is the org ID and a field we call partition. And so the org ID is the unique identifier for that organization. And normally a UUID, or not usually, it is a UUID that's validated from libraries. So when you join the whole cyber grid, you're your user, your customer data is generated, is tagged with this UUID. And then the partition is generally a timed UUID, but it doesn't have to be. And it's our way of limiting how much data goes into a partition. So how do we avoid hotspots? Anybody that's ever run into hotspots knows that it should be a much more graphic term for what that is. It's a painful, horrible situation. So having this allows us to have non-collision in how we're shipping data. We're able to keep a given organization's data separate from a query perspective. And in previous instances, we used a separate key space per org ID, but Cassandra does have a limitation. As you start scaling out the number of tables and key spaces, the cluster becomes, it degrades, right? It impacts performance negatively. So by putting it all in a single key space, the overhead and the mem tables and those pieces is much easier to deal with. The cluster key is just a time UUID of when we inserted that row. So that's all that we need to know about that. And then all of the data goes into the object field, which is going to be a JSON object. So when we're talking about a raw record coming in that we are extracting fields, that's going to create a JSON object. That JSON object will be stored here. So we're not doing any indexing inside of Cassandra. We'll talk about how we do queries and indexing in a second. But so these two form our partition key, our cluster key, and combined, this is our primary key. So when we're doing scans, so if we, for instance, wanted to do a query on a time-based, so everything that happened the last hour, we can do a table scan using the time UUID on the partition as criteria. If we want to, what we commonly do, which I'll talk about in a second, is do a full fetch of the partition, which is a very kind query to Cassandra. We also use compression, which blew my mind because I'm an old guy, and compression used to mean that makes everything slow. But it turns out because our bottleneck is on I/O, on disk I/O and network I/O, shrinking that down in compression has a huge impact on performance. And then TTL, telling it when we're going to die. Always set a default. There is a default whether you set it or not, of course, but managing that on the inserts. So when we're inserting data, there's really three types of principles that we take in this. One is no hotspots, no hotspots, no hotspots. So counting how many rows we're putting into a partition. So whatever the inserting code is, it's counting. That's 1, that's 2, that's 3, that's 4. And then when it hits the max level, it's no longer going to use that partition key. It's gone. And then we're also going to, while we're creating the inserts, we're going to index what is in that given partition. So in the case of artifacts, we're tracking things like client IP, username. So it would be an array, a JSON array of client IP and every client IP that was observed in that partition. And then we're going to save that in the partition summary. So we have one row for the partition in the partitions table, and then we have the artifacts table or different types of objects. And then also setting TTL. One of the greatest things in Cassandra is the free delete. So putting a death date. When is this row going to expire? When is it going to naturally be garbage collected out of the system? One reason we do it this way, where we put the indexes inside of a JSON structure instead of using a natural Cassandra index, is we're looking at 100, 200, 500 different indexable fields. And when we start doing that in Cassandra, we start running into nonlinear scale. So each node gets more expensive if we go that way. So by not adding the indexes, our scope is much smaller. I am sort of excited to see storage attached indexing. It's coming out in 5. We'll be at that talk later today. But that's currently how we do that. So when we're fetching, we start, if we want to get a specific record that says, for instance, give me all of the rows that have username John Doe, that existed in the last day or 10 days or whatever. We start by fetching the partition summaries. So give me the partition summaries in the time range, give me all of them, and check, do those summaries have the criteria in them? So is John Doe in it? If it is, that partition is a candidate for pulling, for doing a full pull on the partition. So then we just, once we have that list, we just go by each partition and fetch the whole partition, and then we just do a reduce of the rows that met the criteria. And it sounds like a lot to do compared to, you know, select all where, where the thing, but it's very effective when you're talking about multi-petabyte clusters of data across, you know, hundreds of indexes. It's a linear search that's predictable in the amount of time that it takes based upon the time range. And it's also very friendly to Cassandra. You're not asking for to stress out Merkle trees and all of that. I'm coming up with time. So real quick on this, when we're receiving messages, we use an approach from natural language processing that has a database of semantic frames. So where does this message come from? How do you extract it? What is this IP address? What is this timestamp? Everything there is to know about the message is loaded into memory on the processor. And then it outputs in JSON format the artifact. If it doesn't know, it goes up and we start doing our research. So we have machine learning. We reach out to the vendor. We figure out what the thing is, and we update the frames. And the reason we do that, I'd love to do LLM here, but it would be bonkers computationally expensive to do that on, you know, message rates of 1 million a second, right? You couldn't do that many inferences currently. So once we have the artifacts, we build a graph out of them. So this is just sort of a pseudo of some extracted field. This is a DHCP lease renewal. This machine exists. It has this IP address at this time. That's its MAC address. Get another artifact that tells us that user 1 is logged into that machine, file Z is present on it. Get some more nodes, some more relationships. Another one tells me that the IP address belonging to client A talked to a thing called server B. So we're tracking all of these relationships. So these artifacts are building a contextual graph of what those artifacts are describing. And then we're also understanding what is the intent. Why did it tell me this? It was telling me this because there's a malware exploit or whatever. So now that we have a graph that's sitting there, and we're persisting that to Cassandra, we're able to analyze the graph. In this case, look for, this is a data theft, a multi-stage data theft attack or crime that occurred. And from this, we can analyze this graph and generate metrics. How many of these have occurred? What types of tools were used? So you're doing graph level, unit of work level analysis. Also, this is just a standard JSON structure, and you know, rendering this is pretty easy. There's a great library licensed under MIT called Cytoscape.js that we use for that. And so now we're just down to moving JSON around to make this magic work, right? JSON's great, compresses great, it has great entropy. You can't do REST without JSON, so you already have now the way that we share information across the internet is in this JSON structure. We can nest data, so that artifact can be that generated the node in the graph can be a child of that. They can be a child of the incident. They can be a child of the campaign, and you can sort of go from the system to the atomic inside of a JSON structure without limitation. And we're also not having to go and do an alter key space or alter database when we need to change or augment a JSON structure. And so there was another talk I gave in Grand Rapids earlier in the year on how all this works if you're looking at the operational side. But you know, we're talking about just sharing JSON objects of incidents, threat intelligence, publication of bulletins. You can publish a job in a JSON format that says search all your data, then give me the results, and then ship that back up to a different cluster when you're subscribing, right? So we're just doing get JSON, put or post JSON, and that can be really any type of information. And then we're just inserting it with that same partition key. So the org ID is unique. The partition is unique from this other cluster. So when we're doing an insert into a different key space on a different cluster, there's no collision, right? So you're able to do the same type of querying that way. And then you're left with the ability then to have this federated system to where you can have maybe universities working inside of a conference that are able to share data and operations with more expensive, more experienced personnel up here, maybe shipping that up to law enforcement when crime needs to be reported. So pretty simple way of shipping data once we think through how do we create the data, how do we collect it, evolve it, save it as JSON, ship it as JSON. So I'll take any questions, but if you want to find my social media or this talk or any other talks, that's me, Charles Herring. There's also the WIDFU blog. If anybody, there's also educational stuff, so if you want licensing to play around with the software, we have that. That's free, and then there's my email. I think I am out of time. I have 1 minute. Does anyone have a question? You may applaud. Oh, wait, there is a question. Yes.
You said TTL and all inserts, right?
All inserts.
The same TTL or different?
So it's a configurable setting. So in a cluster, you may, some organizations, some users may need to keep the raw record for a year or 5 years. So that would dictate what the TTL would be on the insert of the partition or the artifact. So it's a configurable setting. So that's not a universal TTL. It's configured per cluster. And the same thing for the units of work, the incidents. How long do we want to keep those? Those are being inserted. They're also immutable. So it's configurable and are going to change based upon whatever the requirements of the given cluster is.
And what's the compaction strategy?
That's a good question. It's whatever the default compaction strategy is, because of the TTLs, it's a very simple compaction. There's not a whole lot to have to work around on that one. It's the nice thing. It's the way we talked about in the team is whatever Cassandra likes, we're going to do it that way. We're going to make it as easy on her. I don't know if it's her or her pronouns, but as we can. But thank you very much for the time. I look forward to chatting with you guys later. All right.
Okay. Oh, yeah, there you go. You can definitely hear me now. I think the mic might have been a bit overkill for the thanks, but thanks everyone for turning up. And thank you for obviously the millions of people who'll be watching this online. My name is Johnny Miller. I'm from a company called Axonops, and my talk is about our tool, Axonops, which gives you one-stop operations for Apache Cassandra. So, Axonops is essentially a tool that allows you to manage, monitor, and maintain your deployments of Apache Cassandra. And my background and my team's background, we've been using Cassandra for many years. I started using Cassandra with 0.6 when it was like pretty bleeding edge, and we've pretty much had hands on most Cassandra weirdness in the world over the past decade, and we've seen the tools, the evolution of those tools over time. But what we were finding was we were spending a lot of time looking after the tooling to look after Cassandra, as opposed to looking after Cassandra. And there's some great tools out there. You know, I'm a big fan of Grafana, Prometheus, Rundeck, Elastic, all that good stuff. But what we were finding is when we were deploying Cassandra into environments, cloud or on-prem, we would be spending way more time doing the dance around getting the tools working, the tools deployed, the tools secure, the currency of those tools, than just looking at Cassandra. So it's basically hard enough getting Cassandra deployed into a restrictive environment. You come in, you say, I'm going to drop Cassandra in there, I'm going to drop half a dozen different agents, I'm going to open up a load of ports and start sending stuff around your network. You know, we work with banks, insurance, government, healthcare, the kind of places where they're really sensitive about what you drop on their servers. So we decided that we'd take a step back and we'd build a specific tool that gives you, in the strapline, one-stop operations for Apache Cassandra. And one of the call-outs there is we also developed this our own bidirectional network protocol that allows us to communicate, but both in the sense of collecting all the logs and metrics off Cassandra, but also taking that information and acting on it on the cluster as well. So we have one network, one socket, and that's all the logs, all the metrics, then all the control flags for doing things on your Cassandra cluster. So Axonops, if you want to have a little look, there is a website there, demo.axonops.cloud, which is a fully working, deployed Axonops and a Cassandra cluster you can click around and have a look at. And I'll show you the demo as part of the site. And you can see basically the features that we support. So we support Cassandra 3.11, 4.0, 4.1, and 5.0. So we have 5.0 beta 1 running. I wouldn't suggest anybody puts it into production, but you can certainly, we're kicking the tires pretty heavily on Cassandra 5, and as soon as it goes to GA, we will literally be out the door supporting it. And we've done a lot of work to take in the new features. We have specific dashboards and instrumentation about the vector search and all that kind of new stuff in there as well. It also gives you performance dashboards, which you'd expect. A way of looking at all of your Cassandra logs. And we have service checks, alerting notifications, backups, repairs, rolling restarts, reporting. Basically everything you need to look after your Cassandra cluster. But why don't I show you instead? So let me pop out of the presentation. So this is the demo axonops.cloud cluster that I was telling you about. So when we look at the monitoring side of stuff, what we have, when you come in, you see a whole bunch of dashboards that these become pre-configured and deployed for your Cassandra cluster. These are based on our experience, our recommendations about what you want to be looking at, what you want to be monitoring, what you want to be keeping an eye on. But it's completely customizable. Yeah, you can go in, create your own dashboards, create your own graphs. It's entirely within your control. And worth pointing out that the language we use to define these dashboards is we have essentially a PromQL interpreter that allows, so everybody's familiar with PromQL, so we figured why make something else. So we support kind of PromQL type queries for producing dashboards or defining alerts and such across your metrics. We also, on the monitoring side, have your logs. as you would want. So all the logs coming in around your Cassandra clusters. So, and then we have also service checks, and I'll go through each one of these as we progress. So when you start looking at the monitoring side, one of the problems I had was really two things. The amount of data you want to see in a dashboard. Yeah, with Cassandra, there is an enormous amount of metrics that you need. And when the traditional tooling was essentially not really capable of keeping up with the volume of metrics, both from, and what would you end up doing? You'd end up reducing the metrics you were taking off Cassandra. And the number of metrics really correlates to the usage, the number of key spaces, the number of tables. So as the cluster starts getting more usage, you start to get more metrics. And you end up in this horrible cycle of blacklisting lots of metrics. And then when something goes wrong, you're like, I really don't know what went wrong because I didn't capture all these metrics. So, sorry, excuse me. So we can capture tens of thousands of metrics off your Cassandra node, and which is pretty cool, I have to say. And we don't use JMX for this, because what we also found was when you're capturing those metrics through JMX, you actually hit the JVM quite hard, and you actually interfere with what you want your JVM to be doing, which is servicing the requests to your cluster. So we put a lot of work into really efficiently getting those metrics out of Cassandra. You don't notice it happening, and the volume that we can take. And then the flip side of this was the other challenge we have is the precision of those metrics. So when you're looking at the other thing you typically end up doing is reducing the precision. So you say, oh, I'll take it by a minute, I'll take it by 5 minutes, and because you can't cope with the storage. So we support a 5-second granularity of the metrics. We can support even more, but we're kind of like, well, 5 seconds is probably okay. So when it comes to doing the kind of inspection of what's happening on your cluster, you can really dig in to a really, really fine point on what you're trying to look at. And that might sound, 5 seconds a minute, what's the issue? But when you've got like 300 servers and you have to search for something across a 5-minute window of logs and metrics across 300 servers, that's a lot of stuff to be looking at. So the smaller that funnel I can get, the more precise I can get around whatever I'm looking at, it means I can find what's going on further. So we developed a graphing engine that's complementary to how we deal with metrics. So we're able to render thousands of data points, stream them through, and if you're doing this through something like, say, Grafana, I'm pretty sure everyone's experienced this. You're in 3 in the morning, you're dealing with an issue, and Grafana just starts dying because you can't cope with the number of metrics, the number of servers, etc. So we can render literally thousands of servers, thousands of tables, all in a dashboard, and you touch wood, he says, you will not even see those kind of problems. So that was a big deal for us. So when you look at the dashboards, all of these are defined through PromQL. So you would just literally create the prom query for this dashboard. It would again rendered with a select of choices. And the nice thing you can do is, as I said, you can really be zooming in onto the kind of levels you want. And at the same time as zooming in, we also zoom in on the associated logs with that time window. And of course, you can filter across whatever else you want to. So when it comes to looking at, okay, I had a spike, what was happening at that time and that spike, it's all there in one place. And you don't have to be popping out into an Elastic dashboard or something else, and you're not copying, okay, I've got this window here, I've got to go to this dashboard here and copy this window there. It's all in one place. The other thing that we've got on the monitoring side is what we call service checks. Now, service checks are your kind of more custom type of check you might want to run on your Cassandra node. So things like, I don't know, are my SSL certificates still valid? Have they been revoked? Is this port listening? All those type of things. So what we give you there is the ability to create custom service checks with a bash-like syntax. It's not bash. We stop you doing things like rm-rf and things like that, but you can essentially express any kind of check you want to happen on your service, and you can configure Axonov to say, run this every minute, and what you do in your script, you give a non-zero exit code for your check, you get an alert triggered. So we have people using this to monitor other agents that this is running or this port is listening, etc. And the nice thing here is we also template out a lot of the things. So for example, if you wanted to write a service check that's check my Cassandra port is listening, you're not going to type port 9042. You can just put in a template. Same thing with the address. I'm listening on this address. So each node gets pushed. It gets templated into what is the configured values for that server. So that makes it very easy to produce these. And it's very rich. We have clients doing really complex type of checks through this. Then on the maintenance side, there's a whole raft of things you're going to want to be doing with Cassandra. So we provide all of the necessary tools you expect to have from a maintenance perspective. So the first thing you've got, which everybody using Cassandra, it's a really interesting space in Cassandra, is repairs, okay? Now, if you know what repairs are, if you don't know what repairs are an absolutely necessary operational maintenance activity you have to run across your cluster on a regular basis. And it involves a lot of complex scheduling, and managing of that activity. And I've seen every flavor of way you would run repair over the past decade. And we basically said, this is really too complex. So we've developed a tool called adaptive repairs. And what adaptive repairs is doing is essentially, you want to enable it, you toggle that switch, and that is it. You do not have to worry about repairs on your clusters anymore, okay? It is able to, you add new tables, you have different GC graces, whatever happens on your cluster, it automatically picks this up and repairs that data for you. But what it also does, which is the cool stuff, is if you run a repair, typically you kick that off and it's going to, that horse that is out of the stall, it is running. At the same time, you start, it's competing with the resources on your cluster. It's using CPU, it's using I/O, it's using network. Then all of a sudden, it starts to interfere with the performance of your requests. And, what am I doing? Oh, I've got to kill the repair because my 99th percentile latencies have gone off click, and et cetera. And then you're continuously going, okay, now I've got to turn it back on again, et cetera, et cetera. What we do with adaptive repairs, because we have this fantastic pane of sight into what's happening on the cluster, we're looking at the performance and we're increasing or decreasing the intensity of the repairs based on what's happening on your cluster. So you don't need to go in and all of a sudden you have a big spike in requests coming in. Adaptive repairs will slow down or stop, until that goes away. And then once it has the headroom, comes back in, kicks up, speeds on, and keeps the repairs in place, which is very cool. But the even nicer part of this that you get is most clusters, you have a kind of a seasonal kind of workload. You have periods of high load, periods of low load. But the cool thing with adaptive repairs is when your cluster is idling, we take that. We will get ahead of the repair. We'll get ahead of that GC grace. So what that means is eventually, as the adaptive repairs run through their cycles, you're essentially beating the GC grace. And ultimately your data ends up in a much more repaired state because it's naturally being repaired based on what's happening. So overall, you get a much more consistent answer with your data. But and then we also have scheduled repairs for the kind of old school repairs that you do want to do under certain circumstances. Other thing on the kind of maintenance side is rolling restarts. Now you might think what's wrong with a rolling restart? I can just run it and away you go. But when you're looking after 300 node Cassandra cluster and 4 DCs with multiple racks and multiple AZs, if you do one node at a time, you're going to be waiting a long time to get a rolling restart done. So what we have is the ability for you to create really complex restart strategies in AxonOps. So you can do things like restart more than one node in each data center at the same time, or one node in each rack in each data center at the same time, and really build it based on what you're doing. You can really get ahead of that rolling restart and be much more structured in the restart strategy you use. But the cool thing about it is, well, which I love because I hate this, is you often have a change window at like 3 in the morning. And what I can do is I can set up this rolling restart, I schedule it to run, I go to bed, and the rolling restart happens. And then it also integrates with the alerting as well. So when you can have it set up so that when the restart starts, you get a notification. When it finishes, you get a notification. Or if it fails, you get a notification. So you can basically schedule a rolling restart. If it fails, trigger a pager duty, wake me up, come and do what needs to be done. And that's quite useful for my sleeping patterns. And then it wouldn't be much of a database management tool if we didn't support backups, okay? So with backups, you want to be backing up your cluster, yeah? It's one of the things I see in the field on a regular basis. People think just because Cassandra is highly resilient and I can have multiple kind of replicas of my data, et cetera, I don't need to back anything up. That is a fallacy, yeah? Even if you think you don't need to back up your data, you should be looking at backing up your system data in your nodes. And it's really important to do this because it isn't necessarily about, oh, can I rebuild my node if I have something going wrong? It's your recovery time. It's how long does it take for you to get that node back online or that data center back online because something's gone wrong. So backups are really important. It's a database. You should be backing up. But what we do with our backups is you have obviously the ability to schedule backups, schedule the retention of those backups, but also take those backups off server, okay? So we support S3, SCP, local mounts, whatever you like to copy those backups off server. And remember, this is all happening within your environment. We're not taking your backups and copying them into AxonOps. This is all happening within your own infra, your own Amazon, your own Google. So you basically set up a backup in Cassandra, schedule it, runs, and away you go. But the cool thing about the backups is what we do around deduplication. So traditionally when you take a backup of Cassandra, you're doing what's called a no-tool snapshot. And what that's doing is creating hard links to your SS tables. And every snapshot you take, you have another set of hard links to the file system. So what most people do is they take that snapshot and they copy that whole snapshot off server. What we do is we look at the deltas between each of the snapshots, and we only take the changed SS tables off server. And the effect of that is the off-server storage requirements reduce significantly because you're typically not churning through the data at that pace where you have a completely new set of SS tables every day. There's lots of stuff in there. So we maintain essentially that manifest of those SS tables off server. So when it comes to the cost of that storage, it comes down. And we've had people use it specifically for this. You've got like a large Cassandra cluster, you're backing up to S3. Even on S3, it will end up costing you a lot of money. So we solve that problem. And then as you'd expect with a backup, you want to be doing restores as well, and we support doing restores in there. Other thing to point out on the integration side is what do we support for triggering those notifications, triggering those alerts. So we pretty much support everything, yeah? And if there's something you want supported that's not there, let us know, we'll add it. So we have emails, you've got PagerDuty, you've got Slack, Teams, Snow, OpsGenie, Webhook, whatever you like. And the nice thing about the way we set up notifications in AxonOps is obviously you have error as an alert, you trigger an error alert, it goes to that, whatever you've configured for the integration. But we also have the ability for you to override the global alerts with specific domain level alerts. So as an example, backups. Maybe you have a backup team who needs to deal with backups failing. So what you can do is you can trigger the error alert for backup to go to a completely separate PagerDuty, Slack, whatever you like, for that specific team to handle, yeah? And that's quite useful because we find in most enterprises there is a separation of concern on this, or backup failing is a PagerDuty, but it's not the PagerDuty that's going to wake you up in the middle of the night. You'll look at it at 9 in the morning when you come online. So there's often different requirements for what would be a wake me up, something's gone wrong, or don't wake me up, I'll come and look at it in the morning. And we split this up across global, the metrics, backups, the service checks I set for you, individual node stuff, various commands, repairs, yeah? Do you want to be waking up at 3 in the morning if something fails on a repair? Maybe, maybe not. So you can deal with that. And that for me is a killer feature because often you end up with just kind of being blasted with noise on alerts. And the worst thing you can do with alerting is just start sending people alerts that they don't care about. Because what happens is when you get an alert you should care about, you ignore it, yeah? So I'm a big fan of being very, very targeted with when you wake someone up, when you send that error alert, and where you send it to. And this gives us that way of going, okay, hold on, backup alert goes to Slack. Node down goes to PagerDuty. Yeah? you can configure that all up. And the other thing that you can also do is you can set up personal integrations for metrics as well. So you can go into a dashboard and say, I'm personally looking at, say, this metric, this table. If this happens, send me a message on Slack or whatever specific to me. So you have your own stuff you might want to look at, team level stuff, domain level stuff, all in the one place. So so essentially, that's AxonOps, pretty much in a nutshell. So we have performance dashboards, which I've shown you there. We got the logs. You got service checks, which I do quite like. It's because every environment's different. Yeah, there's often weird little things that you need to check for. The alerting and the notification. There's no, anything you want to alert on, anywhere you want to send it, it'll support it. We give you backups, and we have adaptive repairs. Don't underestimate adaptive repairs. It's like, I would say 60% of every guy looking after or girl looking after Cassandra's time is spent dealing with repairs and turning them on and turning them off and recovering and restarting. And one thing to make sure you know in adaptive repairs is when it stops, yeah, it resumes from where it last was, okay? So if you go in and say, turn off adaptive repairs, it will basically remember the state it had got to, the point it had got to with the range of the repair. So when you start it again, it just resumes from there, as opposed to, I've killed my repair after being 90% through it, now I've got to start again all the way through. So it's very good at checkpointing where it's got to in the repairs. Rolling restarts, which you will definitely need. And I didn't actually show you the reporting. So we also have this ability to create reports. And what essentially we do is, where's it gone? Anyways, I'll show it to you another time. So essentially what we can do with reports is we'll generate a PDF report based on a dashboard you pointed at. So what we use this for is essentially you'll have, say, you've different teams who might want to be looking at a particular set of metrics or key spaces or tables, and we can set up AxonOps to generate you a report on the PDFs. And you can then distribute that to your manager, to your team, to say, this is the performance of your whatever you care about. These are the incidents that have happened on this cluster, and that all gets generated into a PDF to send across to your team. So, so there's one more thing. And I forgot my turtleneck, but one of the things that we're really, really happy to announce today is we're essentially launching a technical preview of Apache Cassandra Cloud Provisioning through AxonOps. And what this is doing, it is enabling the provisionance and maintenance of a production-ready Cassandra cluster directly into your own AWS account, your own VPC. And basically, what you do is you go into the SaaS, you provide it with the necessary credentials for your cloud account, and you can then go in, click a button, press deploy, and it will go in and deploy a production-grade, secure Apache Cassandra cluster directly under your own control, your own VPC, your own EC2 instances, your own compute instances, yeah? Not on someone else's servers, not on, so you maintain the control of that data, but you get exactly as good a quality level of service, but it's all running on your own instances. So you benefit from those cloud discounts based on it running on your stuff. You have the complete control around the access to that data, when they can access, who can access it, etc. You don't have to worry about any of those. Often the challenges is all your PCI, your PII kind of requirements around, I can't put this data out onto a shared service. It supports automated scaling, upgrades, and everything you want to do to look after your Cassandra cluster. So here's an example of going in and provisioning a new cluster in AWS. So you go in, you select where you want to go to, we give you the necessary things to set up from an IAM perspective. You make sure you've got everything set up. You confirm you've got everything you want to do. You go in, you pick your access key you're going to use. You pick the region you're going to deploy to. You pick the VPC you want to deploy under. You choose the subnets and AZs you want to be placed under. And then you click next. And then here you pick the number of nodes you want to deploy. Nice little sliding bar to let you do this. And 64 would be a good thing, but we'll go with, I think, probably 6 for this one. Then the next thing you do is you choose the type of EC2 instance you want to deploy onto. You pick ephemeral or persistent. We also give you the cost as well. When you're doing this, the cost of the storage, the cost of the EC2 instance, and then you pick what kind of an instance type you want to deploy onto. And here we're going to pick a whatever. And then the next thing you do is you give it a name. And you obviously need a bastion key as well for allow you to connect up and do stuff. You pick the version of Cassandra you want to deploy. You click next. Out of the box, we'd like you to set up a backup. You configure that backup. It'll create that S3 bucket if it isn't already there. You can give it one. Give you a summary of what it's going to do. You click create. And obviously this is sped up because it takes a little bit longer to start up the instances. But then you go in and hey presto, there is your deployed Apache Cassandra cluster with 3 nodes, and we set this all up, all of the SSL, the key stores, the trust stores, we provision with authentication on, we remove the default super user, we generate a random password. It is now ready as good as you would need in this would be appropriate for a financial institution, anything, the OS, everything. Next thing you get there is, this is quite handy, it's scaling up a cluster. So what we want to do here is increase the number of nodes in our cluster. It's as simple as that. You just literally toggle it up, pick the amount of nodes you want to add, click the button, scale, and then bam, that is it. It now goes in and adds the necessary nodes to your Cassandra cluster, scales it up, and you now have 6 nodes instead of 3. And then the other thing we do is upgrading of Cassandra as well. So simply put, here we're going to do an upgrade from 4.1.1 to 4.1.3. You literally go in, pick the version you want to upgrade to, click update, and hey presto, through the magic of speeding up a video, your cluster is now upgraded to 4.1.3. When we look at those details now, it's all been upgraded for you in there. And then there's another favorite of mine, which is the SSL certificates. No one likes managing certificates, particularly not in Cassandra. And here we make this really easy for you to essentially go in and refresh your SSL certificates. And literally go in, quick refresh, boom, away you go. It's now refreshed all the SSL certificates across your Cassandra cluster. So what I've shown you there is through the cloud provisioning tool, the ability for you to provision a cluster into, right now, AWS. We've got Azure, Google, other things coming down the pipeline. Scale that up and down as you need and perform an upgrade of Cassandra. And there's plenty more as well in there. We support replacing nodes, changing instance types, OS patching as well. So we will let you, you saw the button to patch the OS. We do all that for you as well. When you want to upgrade or patch the OS based on a security, you click Patch OS. It goes in, patches the OS with everything you need. And this is pretty cool. And we're really, really excited to do it. So basically, I'll say this because I work for the company. AxonOps is the only solution for one-stop operations for Apache Cassandra. It gives you everything you need to do to monitor that cluster, maintain that cluster, back up that cluster, and now provisioning as well. And the power here is that you can now very easily, at the click of a couple of buttons, deploy, this is the same level of security, of resilience that we do on lots of clients' clusters into your own cloud account, on your own instances, on your own VPC, all under your control, without having to spend ages figuring out how to do this, how to write all the automation, anything around that. And then we also give you all of the necessary tooling to monitor that. Out of the box, it has all of the dashboards configured for you, the backups that you need to do, repairs, your logs, etc. And we're continuously updating it and adding more and more new features. And it works. And the other thing to also point out on the provisioning side, this isn't just executing a bunch of Ansible or Chef. Yeah, this is stateful. Yeah, you need to be able to running these things in really a stateful kind of flow and process flow around this. So it isn't just, we don't just randomly go upgrade. We are checking things as part of the upgrade. We're going, ooh, something's gone wrong. roll back the upgrade. We have specific flows for, say you're coming from a new major version of an upgrade, we will have the specific steps to support that upgrade. So possibly you need to rewrite all the SS tables as part of this upgrade or whatever. That'll be part of that specific flow for that upgrade path for you. And our job is to put that all that smarts into the tool so you can just basically go there, click buttons, and not have to worry about it and just focus on Cassandra. So thank you very much. We've got time for questions, but just to point out, there's a couple of cool things that you can already go and have a play with. We have our, as I said, we have that demo environment. You can go and click around and have a look. We also have this AxonOps starter program, which is free, basically up for 6 nodes, cloud or self-hosted. Off you go. Use AxonOps, get your Cassandra working. And also, if you sign up now for we're getting quite a bit of demand for the provisioning. So we're operating really a technical preview mode. So if you're interested, scan that QWERTY code, register your interest, and then we'll let you know, and you can come in and start playing with the provisioning yourself. And if you do register now, we also give you a free upgrade to AxonOps Enterprise, which gives you some additional features to what you'd be getting on the free program as well. So, any questions?
Hey, Johnny, on the backup, are you able to compress the export to the S3 bucket, or is it?
Well, actually, typically the SS tables are already compressed. So when you create your once you've provisioned it, you've got to take those certificates and provide them to your applications to use. So yeah, you once it's created that cluster, you can download the JKS and use what you want to do. And you can also copy the CA out to use for yourself to issue certificates. So our thoughts there are you might take that copy of that CA certificate, bring that into your own certificate provisioning environment that maybe you're using that to distribute those certs. So like imagine Vault or something like that to generate those certs, push them to your apps as you need them. So you can download the JKS, you can take the CA yourself, drop it in and use it. Anything else? Stunned silence. Yeah. Cool. Well, so give it a go. Try it out. If you have any questions, there's my email address, johnny@axonops.com, or you can send an email to community@axonops.com. And do sign up for the technical preview for the provisioning and get on the list. And we'll also give you that free upgrade to AxonOps Enterprise. So if there's no other questions, I'll leave it there. Well, thank you very much for your time. I hope you liked it. And enjoy the rest of the summit. Cool. Thanks, guys.
what we can do is, okay, you can move it from here. All right, we get started. Yeah. All right, thanks everybody for joining. I'm Gopal, and he's my colleague Jaideep. We are from Uber. Today we will present how Uber uses Cassandra to power our core applications at a very large scale. The agenda looks like this. We'll have some introduction. We'll touch upon the scale, architecture, and how we manage the fleet. Later, we will also cover some of the features that we have developed at Uber and then push them to upstream as well. We'll also touch upon some of the challenges we face. So let's dive in. We provide Cassandra as a service to our internal teams. We aim to do heavy lifting on Cassandra side and allow teams to use Cassandra with minimum efforts. The first thing that comes into play is how we fit open source Cassandra into Uber's infrastructure. For this, we need to make several changes like service discovery, logging, metrics, change detection, backup. We make these changes on top of open source Cassandra, and we have an internal fork of Cassandra where we make all of these changes. Our journey began with version 2, and since then we have been trying to keep pace with stable open source version. So we keep upgrading as and when possible. As of now, we are almost done with upgrading to Cassandra version 4. Another major responsibility our team has is to understand Uber's needs and develop solutions on top of Cassandra to power Uber specific requirements, and then build those solutions. We push some of these features to open source wherever possible. And later half of presentation will cover some of those features. We also operate the large fleet with lots of automation. We provide consultation to our product teams in mapping their requirements to Cassandra features. By putting all of this together, the Cassandra is made available to internal Uber teams as a service. So let's discuss about the scale. The scale is very large. And at this large, we exercise almost every feature of Cassandra. So when a wide range of use cases are coming into Cassandra at a very large scale, we start to observe weird behavior or sometimes even the bugs. So for example, we are upgrading to Cassandra 4, and although Cassandra 4 is very stable in open source, but recently we started finding multiple issues, bugs, so we fix them and again push them to open source. We use safe deployment practices to catch issues early. We do not encourage customers to do, we do not encourage a lot of custom tuning per use case, because when we are operating at such a large scale, it is not easy to maintain so many custom configurations. So we want to make sure that our default configuration works for most of our use cases. Note that our default configuration is not the same as open source default configuration. So this is architecture. It's very high level, 10,000 feet. As you can see, we have multiple regions. The same cluster can have a footprint in multiple regions. And at the top, we have the orchestration engine that provides hooks where we write Cassandra-specific logic for actions like create cluster, restart node, restart cluster, or replace node. We also use a sidecar that acts as a bridge between orchestration engine and Cassandra. The sidecar interacts with Cassandra using the JMX port. On the data plane side, the applications connect to Cassandra using driver libraries. These are open source drivers. And we make small modifications on drivers, again, for service discovery, load balance policy, host filter policy. The applications only need to provide the cluster name. Rest of everything is done by the driver internally. So this reduces friction in adopting Cassandra into the application side. We also have a hybrid deployment model where part of a cluster could be on-premise and part of the cluster could be on public cloud. Thanks to Uber's low-level infrastructure that abstract out the differences between on-premise and public cloud. That makes migration to and from public cloud very easy. So this is a little bit about the fleet management. We have to have every operation automated. Because of the scale, we cannot manage any operation to be done manually. The fleet automatically reacts to the dynamics of any changes happening. This includes the vertical auto scale, CPU and disk, bad host detection and evacuation. Node replacements to achieve better packing of VMs is also done as part of the automation. All dashboard, metrics, alerts are auto-generated when new clusters are created, so no manual actions needed there. We provide strict SLA to our customer teams. Clusters are grouped into tiers, and SLA depends on the service cluster tier. This is about resiliency and fault tolerance. We have some of the practices that we want to share here. When you book a ride or order food, it is very likely that the order or the request goes through multiple Cassandra clusters, and therefore we need to make sure that the Cassandra is running all the time with highest availability. The bad host detection is very important for us, because as soon as a CPU, memory, disk, network error is detected on the host, the node replacement is automatically triggered, and this operation happens like multiple times a day without even anybody noticing. Next is the replica placement. We make sure that the replica, we never place more than one replica in a single zone, which means if a zone goes down, we will always have still majority of replica available, which will not impact the availability. So if a zone failure happens, Cassandra will not have any impact on the availability. Other thing is the node replacements can be triggered for another variety of reasons, not just the bad hardware. For example, we do fleet optimization. We may be doing some kind of OS upgrades, kernel upgrades, where we don't want to do the upgrades in place, so node replacements are required. And these operations has to go very smooth. The way we do node replacement is we first add a new node, then we decommission the old node. This ensures higher availability compared to decommissioning a node and bootstrapping a node with a replace address option. In addition, we use full repair and node cleanup for guaranteed data consistency. One of the more prominent feature we use is the data bulk uploading. We use Cassandra for feature store used for machine learning. Feature stores are petabytes of data that needs to be refreshed on daily basis. So our ML platform called Michelangelo uploads data to Cassandra using bulk upload. First, new SS tables are prepared on offline using Apache Spark, and then these SS tables are streamed to Cassandra using the storage port. For Cassandra nodes, these streams of SS tables are similar to internode streaming. Marmara framework is used for managing bulk upload of Cassandra. Uber has open source Marmara framework. Now I'll hand over to Jaideep for rest of the presentation.
Thanks, Gopal. So now, in this section, we'll talk more about, what all kind of, features we have developed on, open source Cassandra, as well as, some of the fixes or, corner case issues that we have discovered at scale. So one of the important item is repair, and I do not need to talk or emphasize more about repair because it's essential part of the Cassandra. So I'll straight jump onto what we have done to solve the repair in Cassandra. So when we were looking at building a solution that can scale for the large fleet that we operate, we kind of chose two approaches to run repair in Cassandra. One is of course a control plane based approach where you can trigger repair outside of the Cassandra, and the control plane will kind of manage the whole process of the repair one node after another. The other option we were looking at is having repair built into the Cassandra, like compaction, right? It automatically happens. We do not need to worry about it. So we did a bunch of experiments around it, and then finally we decided to go with having built-in repair in the Cassandra itself. So what it high level does on the right hand side we can see is all the nodes know the metadata about each other, and they actually know like, okay, who is going through repair, and they know the sequence. So once we know the sequence, we can pretty much kind of schedule like how many nodes to go through the repair, and the status is also maintained globally across all the nodes. So what happens is, as soon as you kind of start your Cassandra cluster, very much like compaction, the repair just automatically triggers based on kind of configuration that you have and thresholds that you have set. It has been running like for more than 4 years and pretty much does not require any manual intervention as such. We have kind of taken care of all the corner cases that you can see, like when a node is restart, what would happen if a repair thread is getting stuck in the Cassandra. How do we kind of automatically restart rather than having it manually done. So again, as Gopal mentioned, all these things are available either in form of like some of these are adopted as part of the official Cassandra, or we have like private patches and forks available for you to kind of look at it. So because we are mostly on 3.0 so far, we were using Cassandra's full repair, but now we have moved majority of our fleet to 4.0. So we are actively working on moving from full repair to incremental repair. So another feature or framework that we have built in the open source Cassandra is anti-pattern detection. So Apache Cassandra comes with a wide variety of kind of feature-rich data set. It has the query language is also very feature-rich. It also provides lots of options to kind of end users, like configuration, like compaction strategy, consistency level that you specify as part of your read and write query, and so on. So all those are really promising, and that's one of the kind of power Cassandra is having, where it can serve variety of workloads. But there is a downside to it as well, where what would happen is if users do not data model it correctly, it could lead to anti-patterns like large partitions, tombstones, and so on. Another thing is people do sometimes use like consistency levels like local 1 or 1 as opposed to quorum or local quorum, and depending on your organization's kind of resiliency story, you would have to adjust those queries and patterns. So when we started facing a lot of issues or incidents due to anti-patterns, one of the feedback we received from our stakeholders was like, yes, we would like to know what is the issue, but if we just tell them that, oh, you have a data hotspot, it does not mean anything to them, because you have to be more fine-grained. So what we did is we kind of built this anti-pattern detector in the Cassandra, where we inspect each and every single incoming read and write queries against list of anti-patterns that we have classified, and if they kind of fall into one of that category, you can see on the right hand side that the framework automatically emits the details, and the details is like very fine grained. We provide key space name, table name, partition key wherever possible, clustering key. So it is a kind of structured data. We emit it to our log files, matrix, and once we have the data, we kind of do a lot of other things using the data. On the far right hand side, we can see we kind of have a issue generator which generates. Unfortunately, we cannot fix all these anti-patterns magically on the server side. Otherwise, we wouldn't even have to do all these things. We just apply some magic trick and then it will just fix it. But that's not the case. Like large partitions, some of these are data modeling things where it is not easy to fix it. So we then generate issues, we file tickets and assign it to our users, so they are now aware about what all anti-patterns they have been running into the Cassandra cluster. It is available on the Grafana dashboard. These tickets are this information is very useful when things are running healthy, nobody cares, but when you are kind of running into a scenario where your Cassandra cluster is kind of not performing, or you are in incident response mode, then this is very critical information that you can use, and then in real time it will tell you that, okay, this is the partition key having issue, so basically you can act it fast. These are some of the improvements and fixes that we have done at as Gopal mentioned, right? The scale is pretty high. So what happens is, like, we time to time encounter some bugs or corner case issues as we kind of run Cassandra. So one of the first issues is like token ownership split brain. So in Cassandra there is a concept of storage cache and or service cache and gossip cache, and these two caches could go out of sync in the worst case scenario. So in order to fix that, you would have to restart your node. So but at scale, it cannot work. So what we have done is we have kind of introduced a mechanism in the Cassandra gossiper thread itself, where we compare these two caches, and on demand we kind of fix them, so we do not have to kind of restart a node, and any of those things would not be required. So there is a ticket there. We have submitted a patch here. Go and take a look at it. The next category is node replacement. We do replace nodes like pretty frequently, like thousands of node replacements happen on a weekly basis, and we encountered issues in the Cassandra when we are doing node replacements. So for example, when a node is bootstrapping, and if it fails bootstrap step, then there was no way in Cassandra to know what is going on. So our control plane was just going in the infinite loop, and it would require manual interventions. Another issue we saw was with the orphan hint files. In that case, where when a node is evacuated, but the peer node still keeps the hint files. So what would happen is, eventually you will just transferring the orphan hint files unnecessarily, and over the period of time it will just kind of create a big chunk of your data, and it will slow down your node replacement. All these 4 tickets in the node replacement categories have been part of the open source Cassandra and have been merged with the, so I think you would already be using it, so you might already be getting some benefits out of it. There is a corner case traffic redirection bug we discovered when we were upgrading from 3.0.14 Cassandra version to 3.0.27. So this is again still in discussion with the community. We have submitted a patch there. So if you are proactively planning to upgrade from 3.0.14 to 3.0.27, go and take a look at Cassandra 17248. The last part is the immutable Cassandra. So the idea here, this is a currently work in progress at Uber. So what we are doing here is we have certain use cases where we only write once and then never modify the data. And the write path is again not through the regular SQL port. It is mainly through the analytical workload through the Spark. So it goes via the storage port. So there are 2 things we are solving here. So one is we need versioning mechanism of our data in the Cassandra. That is one. And second is we also wanted to kind of reduce some resources on the Cassandra side. So what currently we are doing as part of this feature is create, dump your data on a, let's say, on a daily basis. You create a new table, dump your data to that table. So today you can create a table 1_December12. Tomorrow you can create another table December 13, and so on. You of course have to kind of expire all the tables. So that automation we have built in. So once you write the data to table on December 12, which is today's table, you do not have to compact it, because then you are only writing it once. So there we are going to save a lot of resources. Again, all this thing is currently work in progress, under development / kind of rollout. So we would kind of provide more updates when we meet next time. The other idea is basically to have a revision. So then you can control how many revisions of the data that you want. One of the ways you can control is through the TTL. Basically, you can keep a TTL, and then you can keep appending data. But then what happens if your analytical workload sometime cannot upload the data, then the TTL will just expire your previous version. So you cannot maintain exact number of versions there. So that's one of the things that currently work in progress. Okay, so with all these things, there are a lot of challenges as well as we operate Cassandra. I think anti-pattern is definitely one of the top in the list, specifically the large partition, because when we have variety of workloads, then you could end up having like large partitions for Uber skis. Like one example, like a larger city would have more rides compared to a smaller city. So if you partition by city ID, then easily you can have a large partition for a bigger city versus a smaller city. So that is one of the challenges we have. As I mentioned previously, we have introduced that framework where at least we proactively kind of notify our stakeholders on such cases, which has helped us a lot, but there is still a lot of work to do, especially in the anti-pattern world there. Second challenge that we have been facing is mostly around efficiency and managing number of Cassandra clusters. So we do have like a lot of tiny use cases coming in the Cassandra that, hey, I just want to use Cassandra for maybe 100 QPS, right? Where for that you probably do not have to create a big or like physically isolated Cassandra cluster. You could end up like having like one cluster and have multiple such use cases, tiny use cases host onto the same cluster. But the major problem is like Cassandra does not provide like well isolation all the way to all the layers, right? So because of that, at least for now, what we are doing is even for those tiny use cases, we try to always create a physically isolated cluster to avoid noisy neighbor issue. And third is materialized view, MV. So it was a kind of blessed feature back in like 16, 17. We onboarded some use cases there, but it was marked an experimental. So we still have those use cases still kind of lingering, and it's not that easy to kind of retire those use cases. But again, we are working on some of these items. This section we are going to talk more about like what we are doing next. So we are currently building a general purpose rate limiter in the Cassandra. So idea here is you might have seen that when you have a Cassandra cluster, you will see like 2 or 3 nodes become hot. So you will see like 3 nodes showing really high read or write latency. But there is a ripple effect where then because of those 3 nodes, other nodes who rely on those 3 nodes will also slow down. So then your entire cluster basically becomes inoperable. So idea here is that we automatically figure out that cluster has all like whether a node has saturated or not. We are kind of probing CPU, Cassandra's internal queues and other information. And then once we get that signal, we try to kind of shed the traffic proactively. So this is currently kind of code complete, and we are rolling it out to production. So we'll once we have it kind of working successful at Uber, we'll as Gopal mentioned, we always kind of create a fork of it, or we always try to merge our changes back to the open source. So we'll create a ticket and provide a patch to it, and feel free to take a look at it. Another item that we are currently working on is context propagation, where when customers kind of use Cassandra, on the server side we are missing the context, because the application context is available all the way from up in the stack all the way to application, but from application to Cassandra there is no context propagation available. Here we are talking about the read and write. For every single read and write query, we wanted to propagate the context. So there is a custom payload flag available in the secure spec, which we are trying to leverage, and this is also an item that we will be working in 2024. We'll be also switching from full repair to incremental repairs and upgrade to 413. That's pretty much. Thank you everyone for showing here and supporting us. Thanks.
Yeah, we can take some questions.
Yeah.
Sure.
No one asked me a question. So, do you work with any of your partners or friends at Netflix and Apple on some of these items that you're developing?
Currently, I mean, we do talk to them like time to time, but some of these items that we have mentioned here are mostly kind of driven within the Uber only. But yeah, we definitely take their help in reviewing the code and the stuff. Yeah, there are I think multiple, so maybe.
Yeah, I saw the slide on fault tolerance and resilience. I was just curious, what are your most mission critical use cases that you're applying to Cassandra?
Yeah, so you mean like what all mission critical use cases are powered by Cassandra? Yeah, so I think we have wide variety of use cases at Uber. So I mean, if you've taken trip or kind of order kind of meal, you can, when you look at ETA, when you look at basically the fraud detection, like legit user, not legit user, so when you open the Uber Eats app, you can see all the feed that is like categorized for you, all the machine learning models. A lot of these use cases have been powered through Cassandra. Next.
So your anti-pattern detector framework, when something gets detected, do you do as a Cassandra team, do you do anything on your side, or you work with the application team, which is used to some of the particular?
So some of the things now, so far we have been mostly kind of just logging it and then filing it to our customers. But now we are slowly changing that course, and some of the things we are kind of taking action on. For example, if somebody provides consistency level of 1, or we generally prefer like local quorum 1, that kind of consistency level. So if somebody specifies consistency level of 1 or something, we automatically switch it to local 1 and so on. Another thing that we are is trying to enforce as much as possible. And now if somebody specifies a compaction strategy, some other time window or something, we try to not honor them and like always behind the scene convert it to a level DB compaction and so on. So slowly we are kind of taking actions on the server side, because that's the best thing. You don't want to rely on hundreds of stakeholders to take action. But wherever possible, we are taking action on it, but there are some cases like large partitions, like data models, we cannot fix it, so there we have to rely on them. Yes?
So I have a two-part question. The first part is, it looks like you are not using any vendor and you are using the open source Cassandra and managing it yourself, which is great. So my first question is, what prompted you to do so, take that route? And my second question is, now that you are already doing it, how many engineers does it take to manage something like this?
Yeah, I'll take the first one. What prompted us to do that? So Uber is not using Cassandra just alone. Uber has its own storage technologies as well. So if you go on the stateful side, we have a variety of storage technologies available. And all of these storage technologies need some kind of orchestration layer to manage these things, right? So if you think of that stateful orchestration layer, that's Uber's own engine developed by Uber itself. And now if any new storage technology is adopted, it has to fit into that, right? So that's the motivation for keeping it. And it helps us to keep every interface uniform, and we are able to scale by putting multiple technologies under the same orchestration framework. Second part you want?
So second question was like, how many people for the Cassandra team you mentioned, or?
How many people do you have to manage this?
The whole, so everything is a separate team. For example, the orchestration is a separate team, is not owned by us. We kind of are the users. So I don't know whether we'll be able to tell exact numbers, but at least for the Cassandra team, I can tell you like it's probably like less than 10 people, managing the whole Cassandra at Uber. Of course, we have to we use our metrics we leverage from our M3 team and so on. So, but core Cassandra and the fleet and everything and development everything is around that.
Thank you.
I think there was a question, or yeah.
So the anti-pattern detection framework, what is the final product? There seems to be a wide variety of detection. Is it like from queries that you find out that application in a dashboard, or the information in the Grafana framework? What is the final output look like? The second thing is that framework is available in
Correct. So the question was like the anti-pattern detection framework, how does it look like in terms of the anti-pattern, and second is like, is it available in the open source? So to answer your first question, high level what it looks like is you can think of like, it will say that, okay, policy ID 0, then it will tell you that, okay, which is, each policy is one of the anti-patterns. So let's say policy 0 is your large partition, policy 1 is basically read, slow reads or kind of tombstones. Then that query, one of the log entry that you will see will have enough details like, okay, the key space name is this, table name is that, partition key is this, and violation is like, okay, the size of that partition is like 110 MB and so on. So it will be that granular, and it is configurable. It can be emitted to kind of log file. It can be emitted to a Cassandra table itself. You can even customize and emit it to your Kafka topic or wherever you want to emit. Along with that, there is also metric also available, which will high level tell you that, okay, policy ID 0, which is, let's say, a large partition, this many large partitions are present, or violations have happened. So that is first part, and second part of your question is, yes, we did, it is at least not merged with the open source Cassandra, but we have our own fork which is published where this code is available.
For the anti-pattern detection, have you ever had teams get like overloaded with tickets like that, or like given pushback, and if so, how did you like get them to like prioritize higher, or like how did you do that?
Yeah, so there are like always a kind of anti-pattern, depending on the type of anti-pattern. If you are dealing with a large partition or kind of tombstones, it is a difficult problem to solve, versus if you are just dealing with like incorrect consistency level or kind of compaction strategy you are supplying when you create a new table, right? So what general first is actually a positive response where at least everybody knows that, okay, what is going on, as opposed to like when cluster degrades, we just say that, oh, we feel there is a large partition, but then there is nothing concrete available. So now at least there is a concrete data available to us as well as to our stakeholders, right? So everybody are on the same page, because which is very important thing when any degradation or anything happens at scale, right? So that is one. Second is there are many stakeholders who have kind of proactively worked on removing some of these anti-patterns, right? Again, it requires dedication and effort, because some of these might take like weeks to months of time. But to be honest, like we have not solved all anti-patterns because it takes time, right? So that's where kind of slowly it is moving towards the right direction and kind of getting some traction there.
Also, it depends on the teams when they assess the risk of that anti-pattern, right? That ticket is filed to them. It is the customer team who decides whether they are willing to continue with this risk or they need to take immediate action, right? We as a Cassandra team cannot help them. We are available for any consultation, but if a change is required on their side, they need to assess the risk and then prioritize that.
And in low-hanging fruits, what we have seen is like sometimes people even dump test data there. So for them, it is easy that, oh, let me just drop this table because it is unnecessarily creating pain. So I think
we are out of time, but we can take more questions offline. Yeah.
Sorry. Thank you.
Thank you. Thanks, everybody.
So when you guys said offline, can I ask again?
Oh yeah, sure.
Let me know, is it good to start? Or yeah? All right. Hello, everyone. Welcome. I got the inspiration for this talk from Buzz Lightyear from Toy Story. Remember the famous catchphrase, to infinity and beyond. So today I'm going to talk about how you scale your application with Cassandra. I'm a principal engineer from Intuit Persistent Service. Intuit is home for TurboTax, Credit Karma, QuickBooks, and MailChimp. Intuit Persistent Service, IPS, we provide persistent as a service that's used by many products at Intuit. We offer two flavors of product. We have what we call Team Manage and IPS Manage. Team Manage is basically, we just give you the code to deploy your infra, while IPS Manage is where we manage everything. So this is a flavor of our products. For example, Cassandra, we support both flavors. AWS OpenSearch, we only support IPS Manage. For Postgres SQL, we support both flavors. But for MySQL, we only support Team Manage. So what is our value proposition for IPS? You see that I'm referring, when I talk about customers, these are service developers at Intuit. If the service developer do deploy the database themselves, you see the activity that's in the dark blue circle that they are responsible for. Of course, they develop the business logic, data modeling, application integration, data lake integration, data governance like CCPA, GDPR, data lifecycle, like deleting your old entities, something like TTL. Data security is like encrypting your sensitive data at rest. Of course, there is alerting and monitoring, scaling, HA redundancy, and multimodal query patterns. Here, what it's referring to is you duplicate your data in multiple databases, the same data, but for different access patterns. I'll get to more deeply. And for Team Manage, when you deploy infra as a code, you see the light blue circle there. Basically, these are the activity the client, we provide either libraries or services and Intuit that the service developer can integrate with. So for example, scaling, HA, and resiliency, all you need to do is just configure, but we provide the hook for you to enable it. For monitoring, for example, we provide basic dashboard. That's important because a lot of people don't even know what to monitor for databases. So we provide a basic dashboard, but we are not responsible for the alerting. They are responsible for their own on-call. Now you see where IPS Manage, where the value proposition really is the biggest, is that really now as a service developer, you don't even care what data you persisted or how you manage your database, right? We are responsible for all the alerting, on-call, your scaling, basically everything persistent as a service. All you're really calling us is via REST API. You don't even deal with the data, the data model that I'll get into. So today's talks, we'll do a deep dive into IPS NoSQL. This is a product within Intuit that's over 10 plus years. It's a very mature product that's serving many critical use cases and used by multiple business units at Intuit. Today, we have 10 production Cassandra clusters. All the clusters are active in 2 regions in AWS. Our largest production cluster is 117 nodes per region, and that could support up to 220K TPS of CRUD plus list API. Our system are multi-tenancy. Usually we stand up a cluster per business unit, some bigger business unit has multiple namespaces or clusters. Our API is relatively very simple. We have CRUD plus list. For example, for list entity API, we only have 2 flavors. We have list by owner, list by index. I'll get into details later. And we have create, update, delete of entity and relationship. And we have both flavors of the API, single and bulk. To read entity, we have 2 flavors of API. For most part, most services is just reading the latest version of the entity. And for those who need like a multiple version to go through the historical version of the entity, we have that API. And for list relationship, this is where you want to find, for a given entity, you want to find all the related entities. This is our overall architecture. You see that the CRUD, our REST API is fronted by API Gateway, where we have the CRUD plus list API. And everything in IPS NoSQL basically is in terms of entity and relationship. So for entity, we have 2 parts of the data. We have attributes, and we have payload. There's a very simple reason for that. The attributes are stored in Cassandra, where the payload can be pretty large. So for that, we store in S3. For relationship, this only has the Cassandra part, that way we store. And for every create, update, and delete of entity or relationship, a CDC event is generated. And that goes to our staging topic. This is our internal topic. And then we have an IPS domain event processor. This event processor, basically what it does is to transform, what you have your raw CDC may not be the most useful for business analysts to understand. So we provide this functionality that you can do transformation from your raw CDC events to something that's more user-friendly to be used. And this, what I call business events, are then forward to domain topic. From the domain topic then, the same events is being consumed by another product by IPS. In this case, I give the example IPS search. So you can see this provides a very powerful system. What NoSQL is really good at is scaling and high availability. But your ability to do ad hoc query is very limited. It's like, well, I want to do a most flexible query, and say, sorry, you cannot do that. So what we provide is a very, with just a few clicks in our UI and the configuration, mapping between the, I'll go a little bit more in detail, is between the logical schema and the search schema. Now data, you have integration with IPS search, and IPS search is backed by open search. Then you can do group by, count by, a lot more flexible query that's allowed. So the same events that's consumed by IPS search then can be consumed by stream materializer here to populate the tables in the data lake. This is where everyone now these days have data lakes where the business analysts do their reporting and stuff. This is an example of the logical schema that this is the first thing our clients that interact with our system comes to define their data model. Here you see the type name here is equivalent to a table name. And you see in this particular entity, student has 2 attributes here, first name and last name. And you see the type here also. And you see the data classification. This is the part that controls the encryption of data address. And the next thing you see here is the index definition. You see here the index here is a composite index of 2 attributes, first name and last name. And you have an option to define whether the index is unique. If unique is true, we'll check for duplicate when you create a new entity. Our index are binary index. It means that we only support exact match. And it's a sparse index, so that if there's no attribute, no index will be created. So this is an example of an entity schema that we implemented. So there are many, many logical schema the user defined. But underneath, we only use one table to persist all the entity. So you see here the partition key here is NS and entity key. NS is just a short for namespace, so that each cluster or namespace in our cluster has a unique namespace. Entity key is just a UUID. Here you see the entity version. You see the ordering here is important. This is in decreasing order because most of our read pattern is reading the latest version of the entity. And then you see the attribute name value. This is just any entity I can store any arbitrary key value pair. And in this example, you see that there are two updates. Our entity version, by the way, is a UTC timestamp. So you see the first update, you have a first name, is Denson. And then during the second update here, you see that a last name is added. This is our index schema. This is the binary index that I was talking about. This is to support the list by index call. Oops. In this case, you see, why is this so jumpy? In this case, you see that in this partition key, you see the index entity type, the index name, and index value. The important part here is the index value. This is, you see that since this is a composite index, you see that the key and value for that particular composite index. And this one has to be a sorted map because you want to, this is an exact match comparison, so that when you want to construct the partition key, it has to be always in the same order, so you cannot, your map cannot be random. So for example, you cannot have last name first and first name switch, then it's not that, you cannot do an exact match. So in our list by index, so the first thing it does is a two-step process. So first, you create the partition key, in this case, right? And then you find all the entity keys. So the first lookup is to get all the entity keys that's mapped to this particular index. And then the second part is to fetch the entities in the entity table given the entity key. And this is our relationship logical schema. You have a relationship type here. And then you define the from entity type. In this case, is a student. To entity type, in this case, is a course. And you define the cardinality. It's basic. Cardinality for relationship, you have one-to-one, one-to-many, or you can have many-to-many. And this is the schema to support the list relationship API. You see here the partition key here is from MS, from key. This is basically when you come and list for the API, you provide the from key. And you provide the relationship type. And you see the relationship type and two entity type and two key as the clustering key right here. So in the list relationship call, you provide the from key, you provide the relationship type, and then I can look up all the related entity keys. And that's what being returned. And then the client usually then we call bug get with the entity keys to get, if they want to get the details of all the entities. And one thing to note here, our relationship are bidirectional. So you will see that this is what the direction type is for. So when I create the relationship, in this case, from student to course, what I call here is the forward relationship. It's the way the user created it, and that's why the direction type is 1. But we also created the reverse relationship. Basically, now, instead of student to course, it's the other way around. It's from course to student. The reason we do this is then you can look up from either side of the node, right? So you can look it up from the from side, you can look up from the to side, and you can look up either way. I always return you a consistent representation from student to course. And something that is also unique about IPS is we implement an internal owner relationship. So every entities you created in IPS is owned. Let's, for example, like user ID. So it helps with the security, right? Because if a user like me own a set of data, and another user own different sets of data, then the data is secure even at the persistent layer, so that another user cannot access another user data, even if the service developer made a mistake. And having clear ownership in this case really helps with the authorization and also securing the data. And we also have use case where to authorize more complex authorization scheme that we have to integrate with Intuit identity system. And the ownership information here is useful for that. And this particular data is also used to support our list by owner API. So a user can come in and list for, like, if you're filing for your TurboTax return, I can see, give me my TurboTax return for this year, for example. These are some of the modeling best practices I've learned. Is don't store a large blob of text in Cassandra. It's very expensive. You think about it, our replication factor is 3 times. You have 2 regions times 6. If you have a large blob, and you can't even search on it, it's really expensive to store it in Cassandra. So for this case, that's why our entity has an S3 payload, and that's why we dump the payload to S3. One thing I noticed, people like to use a kitchen sink pattern. So for example, if our entity schema has no logical schema, I'll put that as a kitchen sink pattern. You put arbitrary key value pair and no one will know what's in your entity table, right? So you want to make sure that you avoid doing that. Another thing I noticed, there are a lot of blogs written that for different access pattern, you duplicate your data. That is very expensive. You can do that, but it's very, very expensive. In our case, like our index scheme, even though it's very simple, it's just a binary index, but it provides an alternative access pattern to the data. But in our case, it's normalized. It's not duplicating the data, right? Duplicating the data, you can do it, but to us, it's super expensive. Of course, you pay in extra read. Now, instead of doing 1 read, you're doing 2 reads. But relatively, the latency is tolerable, right? You're talking about a few milliseconds here. And this is from my experience. You're doing NoSQL for the first time. It's almost guaranteed we do it wrong, myself included. But it's something that you learn. This is our Cassandra setup in AWS. You have 2 volumes. You have commit log. We have data volume that's 4 times 1 terabyte in GP2. There's a reason that we max out at 1 terabyte. In AWS, EBS volume, they give you the max IOPS and throughput at 1 terabyte. If you provision anything more than 1 terabyte, you're just wasting your money. Not really worth it. So just don't do it. Because we use EBS volume, so our compute and storage are decoupled. We like it that way, keep our costs. You can control your costs better, and also helps with the auto recovery. We implement a self-heal mechanism in our infra. When a Cassandra node goes down, it will go down, and it will automatically restart it. So if a server goes down, a new instance will come up. We assign it the same IP, and then we reattach the volume, and then just restart Cassandra. And eventually, within half an hour, the node will come up and rejoin the cluster, right? We don't even have to do anything about it. And our deployment split evenly across 3 AZs in AWS. This is also reflecting our replication factor of 3. So we can tolerate like 1 complete AZ failure in AWS without affecting anything. And this is the time when I give a plug for our open source project. All these things that I'm talking about is in our open source project called DSE Pronto. Many years ago, well, probably 4 or 5 years ago, we had a big effort moving from Intuit data center to AWS. And before, for our tax use case, we were provisioning for each tax year, we provision a new cluster. And that gets expensive pretty quickly. So as a part of moving to AWS, we consolidate this multi-year Cassandra cluster into one AWS cluster. As we migrate more and more data into this new cluster, we start seeing Cassandra ZC pause. You're like, this is the kind of stuff you don't want to see in Cassandra. So we went through, like, head deep down to optimize Cassandra to take care of this GC pause issue. So this is a process that we went through. Here I give out the samples of the settings that we did, that we tested, and then take it to production. So we started with the kernel, and we tested each setting or a group of settings to make sure that we tested and verified the settings that we are putting helps with the issue, not make it worse. So, and the DSE has a very good article reference on this one. And next thing, after we optimize the kernel, same thing again, we repeat the whole process again, testing in each case to make sure that it actually improved performance. Then we move to JVM, from JVM, and then we move to Cassandra, to optimize at each level. If you try to test everything all at the same time, a lot of times you cannot tell if it helps or not helping, right? That's why we are very methodical in our testing to make sure whatever we put in prod is actually tested and help. And the last thing we did was the data stacks driver optimization. One of the things we enable is a speculative retry. This is to minimize any service interruption that can happen. This is pretty standard if you are familiar with the data stacks driver. One thing that to call out here, we do, for example, set the remote region connection to 0 because we don't want to do have any accidental requests to cross region. And one thing that we did, this no host available exception, this requires special handling. For if there's a sudden network interruption, or sometimes I see it even with a few nodes with the GC pause, this could happen. So we have a special handling for that to make sure that our app server can recover quickly. It's basically we terminate all connection to the Cassandra servers and restart everything again. And that seems to make our app server self-heal. Keeping Cassandra healthy is a complex task. It's not an easy thing to do. And this is, our experience from running Cassandra is running repair from day one. Whatever you do, just do it. it really will save you. You don't want to suddenly one day, you have inconsistency and you cannot even run repair. I've seen quite a few cases of those. And another thing to notice is like, your data model, right? In our case, for example, entity, if the client do a lot of updates, then you can see that a white partition can happen. But since we don't expect that many updates, so we lower our threshold in this case, like this compaction large partition warning. The default is 100 megabyte. That's already too big. So we lower it to 1 megabyte so that we can get early read on if something bad is happening to our clusters. The thing is, white partition, when it happens, is very, very hard to clean up. And it affects the performance of your cluster until you remove it. So the earlier you can get notified and earlier you address the problem, it will help with the cluster health. And since we have a logical model too, then during every PR merge, we also review the data model. Like, for example, make sure that our clients don't create silly indices on like Boolean or enum. That basically will just cause a white partition on your indices. And lastly, use any tools you have to help with your operation, like running repair. In our case, we use Op Center. No one did everything by themselves. I do have a very good team, a NoSQL team, very talented engineers that make all this possible. And lastly, we are hiring. Thank you, everyone. Any questions? Welcome to chat. Sure, go ahead.
You mentioned you've been doing this for 10 years. I'm curious to know, like, what did it look like maybe not 10 years ago, but like 5 years ago, because this is like pretty elaborate. So I guess there's been some organic progress.
Yeah. 5 years ago, I think that's the time when we moved to AWS. So that's where we make the huge leap. We paid off our debt because we had to do schema migration also. So that was when I think we paid our debt, and that's when also we see then we also comfortable in expanding our use case. Not use case, expanding our client base, right? Because if you don't have the right schema or right framework in place, it's very hard to scale out. And once you scale out, when now we have hundreds of services in Intuit using our platform, it's okay now because now we have a stable foundation that we build on.
So in all of your earlier slides, first of all, thank you for sharing your journey.
Mm-hmm.
The journey you said, like CDC-based approach you are taking, right? So how you are making sure all type of transactions are propagating as part of your CDC? That from CDC, transactions are not coming into CDC. So how you making sure, or you are restricting to say like they can use only some type of transaction, or something like example, counter or live transaction. Those are not coming into any CDC file. How you making sure those are propagating?
So we are not using Cassandra CDC. We use our internal. Cassandra CDC is like, we don't really like it. So we implement our own CDC, and we kind of do a pretty cool stuff with our CDC. So we use Kafka for our eventing, but as a resiliency to make sure that for every create, update, and delete, right? We don't want to miss any events. So basically, we have two systems. Basically, we use Kafka, and then as a backup, we use SQS as a buffer. So for most part, if Kafka is up and running, we will use Kafka. That's our first choice. When Kafka is not available, we will post to SQS. So that we, if any system is one is down or the other, we are not affected because if something is down, we did have outage on our managed Kafka within Intuit. Our SQS buffer kind of saved us. And because it was down for like a few hours, everybody was crying. But having the resiliency we built in, it helps that, we don't need to do anything when the Kafka is up and running again. Our buffer from SQS start flowing in. Yeah, go ahead. No, Kafka is more like a post events. So if, for example, if Kafka is not available, I post to SQL. So it's independent. So the transaction is always taking priority. So for example, if both systems are down, unlikely, we have transaction logs that we can go through and replay. That would be the last result because that's it's not automated. It's more like a manual task that we can run. But we do have that option.
You said you offer monitoring, I would assume, particularly to your DIY internal customers, like a dashboard for monitoring.
Yeah, we do.
What's that based on?
It's based on wavefront. So we use Telegraph to collect the matrix. And we also have matrix that from CloudWatch also, that everything then get forwarded to Wavefront, and then Wavefront is where we surface our build our dashboard, and also build our alerting into. We use Op Center for very Cassandra specific things like note down, that kind of thing. Right. I'm wrapping up here. If any question, I'll be on the side. Feel free to chat with me. Thank you.
No, we're actually going to go with a handheld, and he's looking for a clicker. So,
The state of the community.
yeah, in my element, I'm a wanderer. That is my preferred mode.
For whatever reason, I'm remembering, what's that called? Jerry Springer. So I'm just expecting you to walk around and like, so who do you want to punch right now? Okay,
That
here's the
was a lie.
Wow, the idea of like that being the community, like state of the community, and it's like
Wrapping it?
you are not the father style.
What's that? Here's here to assess. USB-C or USB?
USB.
I've got a adapter for that. Hold on. Oh no, actually there's USB on the belt.
Dongle.
Yeah. I got it. You're at an awkward angle.
You might have to click OK or something like that.
I don't wanna. Why are you doing this to me? Okay.
Oh, it's working. Oh,
Yeah,
there
it
you
is.
go.
Awesome. Thank you. Spoiler alert.
I'll just leave this here.
Thank you so much. We will let people filter in. So I get to wander. I have a tricky outfit, I was told. So I'm going to be walking, and I got a clicker. I'm happy about all this. So. Yeah, apparently getting a clip-on with a hoodie. I was laughing about that yesterday. I packed 3 black hoodies, and I'm like, how on brand could I be? I even bought 2 differently colored hoodies last week to not do that. All right, I don't see anybody straggling in. So I'm Josh McKenzie. For those of you that don't know me, I'm the one that writes way too many emails in the dev list that are usually way too long. Currently PMC chair, committer. February will be 10 years on Cassandra. Let's just acknowledge that. It's a long time. Went from 0 children to 2 children in that time frame. So it's a good time. It's good to grow. I'm going to be talking about the state of the community and a variety of different metrics that I pulled out from both the Git repo and looking at a lot of different things in terms of engagement, in terms of, for folks that are connecting with the project, what does it look like for them, and how are we all doing? Like, what's our history look like together? There's a TLDR, which is that the state of things is good. I like to think of this as, you know, the quotation here is, it resonates with me. I was just joking with some folks like last week about training a model to spot the amount of gray and white in our hair and beards to kind of get an idea where we're all heading. But like, there's the question of whether you get better with age or whether you become brittle. And I was actually thinking about this last night. My neighbor, who's in his late 30s, took a dive out of his shower last month and like face planted on his sink. And he sends me a text message with his face all battered up, and he's like, I look like somebody from a video game now. This is great. I'm like, dude, no. You need to go get stitches. And so that's the whole, like, as you get older, you got to be careful, right? You got to be delicate with what you do and with the risks you take, and you got to be smart about it. And I think all that actually applies to our project and how we work with things. But you can't atrophy, obviously, as we all know. So the Apache way is community over code. So we're going to talk about the community first, and then we're going to talk about code second. You're all very literate, so you can see what's up there. But we're going to kind of funnel our scope in terms of whether we're talking about the big picture, the small picture, and kind of have a flow to it, hopefully. So for the community itself, this is the lifeblood of an open source project. And you all know that, and we can all say that, and that's like the great little, we put it on a mug. But the reality is, like, unless we have robust diversity across a bunch of different stakeholders, we're at real risk, right? Like, something can change. All it takes is a change in the market, a change in a company, a change in one space. If you got a single point of failure, your project's gonna be dead in the water. So that is a thing that we crucially have to avoid, and that's kind of the backbone of a lot of the philosophy on the Apache side, is how do we make sure we have a lot of different, egalitarian, meritocratic, balanced contribution from people. So let's talk about it. All right, so unique contributions by year. This is a breakdown from our illustrious repo, removing merge commits. I don't like them, but that's fine. We can all talk about that later. There's a pattern that we see here that you're going to see again and again, which is an uptick through 2016, a downward trend, and then a climbing back up. And there was a broader thing happening in the Apache Foundation and a lot of different projects through this time frame, where in many ways the projects, the participants, vendors, the foundation, we're all kind of trying to figure out how do we all play nice? How do we all work together? How do we make sure that folks that are being funded to work full-time on a project aren't completely skewing it, or there's too much concentration in one place, et cetera. And so there was something of a kind of broad, I would say, correction in 2015, 2016 across far more than just the Cassandra project, where a lot of us had some things to learn in terms of how we were structured. So what we do see is the trend going on from probably about 2019 onward, where we are at a healthy place steadily climbing upward. And if you look at our commits, which is a terrible metric because TCM just merged, and it was one commit with 88,000 lines. So anyway, we all know this is a terrible metric. But if you look at enough terrible metrics together, maybe you'll find a fit line that you can tell a story about. But basically, we see the same kind of trend, where the velocity of the commits coming into the project, there was a back off, but then we're climbing back up. Now, we'll talk about this when we get to the releases. There's also the 4.0 timeframe that took place in here that we will discuss and the effect that had. So another one I thought was interesting was per email address. How many times are people committing? I'm guilty of having, I think, 3 email addresses in the history before I settled on the jmckenzie@apache.org one. So there's that kind of an issue that would pollute the data. But there's a question of, do we have individuals that are pushing a huge number of commits? And I always joke about Dave Brogis. Those of you that don't know, he would just ninja tons of spell corrections and comment fixes in there. So he always showed up with all these commits, and we're like, Dave's never talking to anybody. What's going on here? But we have a cleaner code base for it. There really doesn't seem to be a big change in terms of, for each individual that's actually working on the project, on average, how many commits are they actually putting into the system? This is an interesting one. I wonder what it means or what it entails. Cassandra is not the most accessible code base in the world. So if somebody coming along and on average we say most contributors have 4 or 5 different commits, what does that mean? Right? Does that mean there's 4 or 5 big commits? Are they 4 or 5 small ones? And then they're like, oh my God, my brain hurts. I don't know. But we can chart the whole, how many contributors do we have, and on average, how many commits is each contributor pulling in? And as it turns out, we're actually fairly steady. So the number of people that are participating in the project is growing, and the amount people are engaging seems to be staying relatively steady. I take that as a sign of health, but also there's an opportunity to grow here. There's an opportunity to encourage folks. There's also an opportunity to look at all the tickets that are stuck waiting for review, that all of us have, and figure out how we unstick them and stop the rebase hell. So conversation-wise on DevAt, looking since about 2020, how much are we talking? I probably should have removed myself from this graph because I'm sure I've skewed the thing. My role in many ways is often, if I hear something from 3 different people from 3 different places, I'm like, okay, this has got to be a pattern. Let's all talk about it. Let's all chat about it on the mailing list, and then we end up where we end up. But we've been getting more and more engaged over the last few years as a project, communicating with each other and kind of hashing out. I know bringing the CEPs onto the dev list had a big impact on this as well, where we're actually talking about what we want to build before we just build it and drop it on each other, which is a plus. So that's a good sign. The user at mailing list has been getting quieter and quieter over time. This is an interesting one. I wondered about this. I talk about it a little bit more in some of the subsequent slides, but one of the things that has set Apache projects apart to me is that holding to the whole, if it didn't happen on the mailing list, it didn't happen mentality. And I get it, right? If somebody has a conversation in a Slack thread, not everybody sees that. And there's an accessibility problem, there's a archival problem, there's a, if it didn't happen on the mailing list, there's no way to know everybody in the ecosystem had a chance to actually engage. That's not as true for the user list. Like a lot of governance and voting and discussions of that sort aren't taking place in this domain. So the question for me would be, are the users not feeling served by the user list, or are they congregating somewhere else? Not that I'm bearing the lead there. The Cassandra channel on ASF Slack, and I sampled these numbers a few months ago, pretty healthy. It's got some decent velocity on it, just short of 2,000 people then. And then when you look at Planet Cassandra, I had Patrick actually eliminate all the idle accounts from there. We had not quite an order of magnitude more people on the Planet Cassandra Discord server than the Cassandra Slack. Now, a spot check of these two systems showed about the same level of conversation. So there's that whole argument of, well, getting onto the Apache Slack, you gotta actually get invited, and there's a challenge there, and people will bounce off that. But the people that end up going through all that may be more motivated to actually engage. Either way, for all of us that are working on the project, we are well served to engage with our users wherever they are, whether that be Planet Cassandra or the ASF Slack, and help them as we can. One of the things that's been very enlightening and humbling for me is working with users and hearing their feedback about code that I've written. And I'm sure all of us have had that same sensation where you're like, well, why would anybody ever use it this way? And it turns out most of them do, and you were wrong. So anyway, my bid here would be, if you're not on the Planet Cassandra Discord server, actually get on there. If you're not on the ASF Slack channels, for sure get on there, please. And let's just make sure that, when users come forward with questions, if there isn't an obvious place in documentation to point them to, there's something we can learn from that. If there is an obvious place, we should help them navigate towards that. Like, we need to kind of work on these on-ramps for our users just over and over. This has been, our white whale for years. So a vanity metric. A lot of people love DB engine rankings. This is wide column stores. Cassandra steady. Like, we've got a niche. We've got a place that we excel better than anybody else. There's trade-offs that come with a primarily Paxos-based, Dynamo-based system. But the things that we do well, we do like nobody else, right? Like the availability characteristics, the scalability characteristics are pretty rock solid. Like that need is not going anywhere. And I've been making this argument for, I don't know, probably 5 or 6 years now. There's kind of a race between how much data set sizes are growing and how databases are accommodating that growth. And a lot of people start butting up against architectural problems when you get into really, really big multi-terabyte, petabyte data set sizes. And we're just moving to more and more and more data. This entire conference, there's half of it that's like, hey, here's Gen AI generating a bunch more data. So I don't see this really going anywhere or changing anytime soon. So yeah, we're in a decently healthy spot in terms of the place where we exist and the places that we serve. Now the introduction of, and we'll talk about it a little bit later, Accord, multi-partition atomicity, the introduction of vector search, we're starting to kind of elbow out of our niche a little bit. But we'll look at those vanity metrics when the time comes. So ecosystem-wise, we've had quite a lot of change this year in terms of how we as a project are kind of positioned and how we relate to different sub-projects. We didn't really have any rules to work with sub-projects before. We didn't really know, like, okay, how do we vote on things? How do we release things? If somebody's working on something, like the driver, for instance, like who would be committers? How would we bring them in? We didn't really have a map for that. So in the last year, we've actually ratified some rules to know, here's how we bring new projects on, here's the number of PMC members that have to represent those projects, here's how you become committers on them, here's the social contract. And since that time, I've come to realize there's a bunch of Apache projects that deal with this exact same thing and already have prior art in this space. And there's just this constant like turning of the wheel of, there's the old timers with the wisdom that say, well, here's what you'll run into, and here's the problems, and here's how you should do it. And we're like, hey, we just rediscovered fire. This is great, guys. So it's heartening to see that what we're doing it rhymes with what a lot of the other Apache projects are doing. And there's a tension between bringing on these sub-projects and not becoming a foundation or an umbrella yourself. I don't think we're at any risk of that, right? Like, nobody's gonna run the Cassandra sidecar without Cassandra. That's not a thing you do. So this has been really good to see. We've had a lot of committers come in recently on these side projects. Since I originally pulled this presentation together for a town hall, the driver donations came through. And that's a huge amount of code, of work, of history There's a bunch of contributors that are going to get pulled forward as committers on that because they wrote a bunch of code, and that's how we recognize those contributions. Yeah, and it's going to be interesting to see how this evolves and where we go now that we've got an easier on-ramp for folks who are like, hey, I worked on thing X. You know, I've talked about there's a Planet Cassandra website, and there's a question of, okay, why isn't this under the foundation? Why isn't this a sub-project? And immediately the response from the folks that are maintaining that was like, that would be awesome, please, I need more help maintaining it. So we kind of started need to start thinking about, beyond just the core database itself, how do we grow our ecosystem? How do we grow this umbrella and have more people underneath it that are part of this ecosystem, that contribute to docs, that contribute to the website, all these other things. It's getting a lot better, for sure. Integration-wise, we've got a bunch of integrations. These are some of the more robust, well-known, mature ones, but you can find stuff all over the place. There's a boatload of different integrations out in the wild for Cassandra. So just had that in here so you can. All right, so the committee itself. As of 2023, we have 73 committers on the project and 36 PMC members. To me at least, it's surprising how many PMC members are active out of that 36. And I say active from, like, we do a roll call periodically, so we know, okay, when we vote, what does a majority even mean? Like, how many of us are following the mailing list? How many of us are staying involved? And it's a good number. So there's a lot of folks that care a lot about this project and that have stayed connected. Some of us have floated away from the project briefly or for longer times and then ended up coming back into the ecosystem and just kind of can't get away. And it's heartening to see that what we're doing is keeping people engaged, and it's keeping them caring and, you know, fighting the good fight. So community-wise, I think we're doing pretty well. We're doing better than we have in the past in terms of bringing on new people and in terms of encouraging connecting. And part of the, I guess, question to me, like, proof is in the pudding. Like, what does that lead to in terms of outcomes? If your community is healthy and strong, then what? Well, it turns out the thing we build it. It's amazing how that stuff all works together. Fun fact, when I was digging into all this stuff for the presentation, there's letters between Ada Lovelace and Charles Babbage where she's like, you need to stop trying to correct my math. Like, let's focus on, like, what I'm saying, not you trying to nitpick me. And it turns out she was right and he was wrong, which I found delightful because that reminds me of our mailing list. But, all right, so releases-wise, this is a fun one. I like this one. There's Mount 4.0 in the middle. So this is a chart of how long it took us between the previous major to hit the next major release. And one of these things is not like the other. So as many of you may know, for those of you that don't, you'll get a little history lesson here. Cassandra first started out as basically a schemaless thrift-based database. And the storage engine was not really a storage engine. It was kind of like YOLO, do whatever you want. And it turns out a lot of people had a really hard time with a proliferation of effectively schemas and structures and, like, micro storage. I mean, the storage engine was its own thing, Aaron. It had its own code. I see your face. But you know what I mean? Like, thrift didn't have strong opinions. You could do whatever you want. And a lot of people found it got out of control really quickly. And they had a really hard time figuring out, okay, what is in here? How do I pull stuff back out? How do I introspect? This was actually before my time, so long time ago. But that's baked into the bones of the system, or at least it was. And we moved from thrift to CQL, but there was kind of this kludgy, painful translation process that took place. And then the storage engine, we moved from kind of a thrift-first structure, logically, to a CQL-first structure, logically. And that's where we kind of discovered a lot of dragons and demons and skeletons and all the things that come along with doing a major change in flight, right? Like, that's the reassemble the engine as you're going down the highway at 100 miles an hour. What we ended up doing for that 3.0 to 4.0 period was investing a huge amount of energy and resources into testing the system and sussing out what's going on with the storage engine, where are the edge cases, where are things falling apart that should not be, how do we get to the point to where we have the confidence in this system that we had prior, but now the confidence is actually backed up by empirical evidence as opposed to hubris. So that's where we went there. Part of that theory was go slow to go fast. And this is a thing that if you're following the dev list and participating, as many of us are, there's a tension with every discussion we have about, do we hold to a release every 12 months, or do we release when we have specific features or specific functionality we know that are going to be hugely impacting to our users? There is zero right answer. And this is something that I often say it took my wife, Melissa, about 10 years to drill into me. Nothing's black and white. Like, there's zero right answers. It's all in the middle and, like, compromise and, like, disappointing gray space. I'm like, great, thanks. I want a clear answer that I'm like, oh, here's the right one, let's go. That's not how it works. So each time we come up to a release, much like we did with 5.0, much like we looked at with transactional cluster metadata and Accord, there's this unknowable question of, we had a big gap with 4.0. How much does the world care? How much do our users care? Would they want to wait 6 months or another 12 months for a release that had features? Or do they look at it and say, you guys did all right with 4.0 and 4.1, or with 4.1 rather, but 4.1 is one release, and before that it was like 4 years. So I don't know. I don't know what the answer is, and none of us do. So we've gone back and forth, and we've kind of tried to figure out the right compromise for this. And in practice, this is where we reached the point where we said, look, if we cut 5.0 right now, and then these features are available in early 2024, we can cut a 5.1. And it's like not that big of a deal. It's not the end of the world. The pain comes in with certifying releases. So certifying Cassandra is a big, big lift for places that are running a non-trivial amount of infrastructure. And for folks that are looking at the ecosystem, they're going to have to make this decision about, do we validate and certify 5.0, or do we wait because we know we're going to be needing the features that are in 5.1 and build based on that? Again, no right answers. So this is something that the release cycle of our database has really kind of baked in and shows this tension and this struggle that we've had kind of collectively as a group. If we look at number of JIRA resolved per year, again, this is just like the TCM commit, where not all JIRAs are the same. But interesting metric, same pattern, spike up, drop down, growing back up. Everything looks like it's healthy. Looks like we're bouncing back, looks like we're recovering. The new feature JIRAs, I put this one in here because I was curious about whether or not from a new feature perspective, we're starting to bounce forward. We are. We have a lot of stuff coming in. There's a lot of things happening in the Cassandra world. It's interesting how that happens. All right, so numbers don't tell the whole story either. 4.0 to 4.1 was a pretty modest change. And there's a bunch of changes in guardrails and denial listing, and I promise I didn't just put those two because I worked on them. I really was looking at 4.1, and I'm like, what did we do in 4.1 in that year? There's a lot of stuff in there, but in terms of new feature tickets inside the system, there really wasn't that much. Whereas 5.0, we've got a ton of stuff that came in, right? We've got the CIDR filtering, we've got the trie-based data structures that Branimir put in there, SAI, a little thing that we've talked about in vector search, the UCS, the Unified Compaction Strategy, MTLS. 5.0 is a pretty freaking huge release in its own right, independent of the revolutionary monolithic elephants in the room that are us going away from gossip and moving to a new novel state-of-the-art Paxos implementation. So it's kind of like we went from famine to feast in terms of the features in Cassandra, and that pendulum swing, we're incentivized, I think, right now to make sure that we are careful about what we do, that we are deliberate about validating the correctness of these features, about making sure that the characteristics and the properties that the database proposes that it has, we actually adhere to. Kind of an important detail when you're the backbone of a huge amount of the world's infrastructure. So the transactional cluster metadata and Accord I have here as fast follows for 5.0. That was the whole debate of, do we just push 5.0 until they're ready or not? When do we do this? There's that kind of float that we need to figure out. And honestly, it's been a decade, and this is the same tension we face with every release, which is, but we're so close to this thing, should we wait for it? And we have no idea, and we don't know what the right answer is. So the CEP process, we used to have this structure where oftentimes you would get kind of a bomb dropped on you, where as a community, you'd be going along and then all of a sudden a JIRA would open and somebody would be like, hey, here's this .patch file, and it's like 47,000 lines of code and it does this thing, and everybody's like, wait, what? Hold on now, I am uncomfortable with this. In the early days of the project, that worked fine, but as more and more people adopted it and the stakes got higher and higher, more and more you're like, well, hold on, my whole job is based on Cassandra doing well, and if this destabilizes my workplace, I'm going to have a bad time. So how do we move away from all of these surprises and also move away from people doing things in isolation, people duplicating each other's work, people having 4 or 5 different sidecars existing all across your ecosystem that nobody's talked about? The CEPs have actually, I think, proven themselves. They're accelerating. People are engaging with them. We've seen names that we have not seen before. We've seen new contributors coming forward and proposing CPs for things. That to me is the real mark of health, right? If it's somebody that has been, putting tens of thousands of lines of code into the database over the last decade, it isn't that surprising to see a CP from them. But if it's a new name where they're like, here's a thing that I really have an itch to scratch and I want to work on this and I understand it, that says something different to me. And we're seeing that. So I consider that a good sign. I've got to give like at least two clicks. So CI, my personal emotional and psychological burden. The CI in our system is complex, and it is growing, and it moves in one direction. It just gets bigger. Nobody ever trims it down. Nobody removes things from it. And this is something that I have a personal belief is becoming more and more of a burden that we're all carrying and slowing down our work. Now, all that being said, we're making an immense amount of progress. Mick has done a ton of really, really incredible work on this space to try to get us to where we have a turnkey, repeatable CI system that anybody can run. I've been working in this space as well myself to try to move us towards a declarative structure where anybody that wants to build something out, they can just kind of socket together the puzzle pieces and just run it. Back in 2021, we introduced this thing called Butler, which lets us look and say, like, over time, for a given test suite, how does it look? Is it flaky? Does it fail consistently? What do we look like for each branch? We got a single pane of glass where we can look at all of our different branches and basically say, are we trending in the right direction? Or are we trending in a bad way? The build lead role we introduced in 2022, we've had kind of mixed success with that. For the first probably 6 months or so, it was definitely very focused. We have a person signed up, we're doing it. Then there was a bit of a lull, and now it kind of feels like there's multiple people in the community that are kind of carrying this burden. So that makes me a little uncomfortable, just because like I want them to be happy doing things, not necessarily feeling obligated. But anyway, that's neither here nor there. I want to make sure that we find a sustainable way for us to continue to kind of tie A to B in terms of if we have regressions, if we have failures, are we triaging them? Do we know that they're taking place? Are we figuring out whether they're actual product defects? And how are we closing that loop? So the repeatable CI is in progress. There's a Jira you guys can take a look at if you're so disposed. And we've moved the CI scripts in tree. This is something I think is a lesson we've all learned over the course of the last few years. Things that are not in tree with Cassandra may as well not exist for a lot of people on the project. Because you're like, I'm not really sure where to go. I'm not sure how this links up to that. I don't know what pulls it down. So I'm just going to keep doing my thing and hope that me not knowing that isn't going to be a big problem. So I think we're going to move away from that. I think we're not going to like mono repo the massive, I don't know if it's Google that has that, but anyway, our ecosystem is not big enough that this is going to kill us. But I do think it's going to be good for us to get a lot more stuff like Harry, for instance, into the tree proper. So all of us, it's like right next door. It's in your IDE. You stumble across it when you're looking up symbols. All the ways we enjoy discovering things in our system. So if our community is doing well, and it is gradually and gently growing, if the code is going all right, and we're getting back into a release cycle, another question is, are we behind the rest of the world? As a database, are features just making up room for things other people have already done, or are they unique and novel? So as it turns out, we have a lot of novel stuff. Like that's the spoiler. I'm gonna keep clicking my button. Is it worth it to have the clicker if it doesn't always work? All right, so TCM, I'm obviously not gonna go into deep technical detail, but gossip has been an albatross for us for years. And it isn't necessarily gossip's fault or anybody's fault. It's just the whole, like, at the time it was the right choice and it worked well, and it has worked well for years, and there's better ways to do it, right? Like the trade-offs that come with that implementation in that system have proven to be untenable, unmaintainable trade-offs for us all. So TCM really moves us towards a much better posture when it comes to our ability to, like as Alex said during his talk, move towards a much more elastic system, move towards being able to be much more deliberate about what is housed where, why we put it there, on what scale we actually do that addressability, and at what times. Whereas we're not there right now, obviously. At the end of the day, like what people care about, bootstrapping more than one node at a time, some people actually want to do that, turns out. Expanding and shrinking, anybody that's run a cluster and has done a shrink, you know what I'm talking about. There's some pain there. Like there's a lot that you got to babysit. There's a lot of hand-holding you got to do. and gossip plays its part. You know, if you're an on-call shift, it's probably like at least a 50-50 roll of the dice if something bubbles up, if it's gossip related. Like it's, yeah, it's fun. So TCM, like just that piece of it, super exciting. SAI. Secondary indexes for a long time have been the thing where when someone's like, what should I do with it? The answer is disable it. And people are like, wait a minute, what? It's the same thing. We're like, what should I do with the triggers in Cassandra? Don't use them, right? So that we have a lot of things that are in there because they were useful at a point for a use case, but unless you've got a lot of people turning the crank over the years, they don't get the TLC over time. Secondary indexes aren't really that. It's more of like this architecture only goes so far and it is not as far as anybody needs it to go. So SAI fixes a lot of those issues. To me, one of the most telling things is kind of right here, the graph of size on disk of indices. For those of you that were around for the launch of materialized views, for all the railing about whether or not the data was correct and whether we've orphaned data and how we rebuild it and the fact that we just couldn't answer a lot of those questions, the real killer was users would add materialized views and not realize it was going to exhaust their disk space, and it started killing nodes. And they had no way to know. So disk space utilization that's under user purview with no way to predict it, like that's just a recipe for pain. So SAI is very nice to your disks. This matters. And it's good performance, and we need indexing and all the other things it does. Like all that stuff is super, super important too. But at least for looking at some of our previous struggles as a system, when you're working with data at scale, like you can back yourself into a corner when you have terabytes and terabytes or petabytes of data where you're saying, crap, I got an ETL within the own system because of what has happened and how it has transformed over time. So I think SAI is in a really, really good place. And functionally, like the amount of different indexing that it adds is really, really nice. It's really good. So ANN vector search. For those of you that know anything about the ML space and Gen AI, a big piece of what people are looking at doing is how do we move away from just trusting what these models have baked in and instead have it feed me back information that is relevant to my interests, right? Like if I take my own data set for my business, or if you take your own code base and you want to know where things are, you don't want to just ask like the sum of all human knowledge they have baked into this cloud. You want to ask it for your use case, and that's kind of the whole point. So the disk ANN algorithm that we're using in Cassandra and ANN search is fast, as it turns out. And at least as far as I know, there isn't really anybody that has a credible story about a horizontally scalable, elastic, always available data store that can hold as many vectors as you want to throw at it. So that puts Cassandra in a fairly unique place at a time when there is more than a little bit of interest in a certain space. This builds on top of SAI. And this, at least in my opinion, fits pretty well with our architecture. It's not the kind of thing where we're like, are we just adding something because it's in vogue? That's not what this is shaped like, right? Like vectorized data is useful and has been useful, and there's an immense amount of interest right now. But even if that interest wanes, which most people don't think it will, this is still a valuable thing to have in Cassandra, worth maintaining and state of the art. So, Accord. I am not going to do a disservice by trying to get deep into the explanation on the technical side, because this is one of those where it's like you read the white paper and you're like, I understand some of those words. This is great. There's a lineage in Cassandra. There's a tying of our wagon where we've hitched ourselves with Paxos, where we basically say, look, there's Raft. It's out there. It's a great algorithm, but that's not the algorithm for us. Here, we play Paxos. And then you look at the lineage of Paxos as it's evolved over time, as it's gone through ePaxos, which Blake was playing with years and years ago, and much like his refactor out the static singletons, everybody's like, Blake, your patch is very large and very exciting, and I'm scared of it. So this has been kind of his white whale and the crank he's been turning for many, many years. Accord is a novel extension beyond where kind of the state of the art in published research was, and moves us towards a place where we can effectively have one round trip on strongly consistent activity on our database across the whole system, right? And so that's a kind of an unheard of like opening up of multi-partition flexibility. And for those of you that have worked on Cassandra for a long time, maybe you're like me, where your first thought is, oh no, how are people gonna use this at scale in a way we never expected that will be very painful and blow up when they have like terabytes of data and they manage to make everything collide. So we're gonna have to figure out like what's the right way to get this to scale, what's the right way to set up guardrails. We have all these things in place, and we'll learn as we go and work with our users. As far as we can tell from our testing and from the proof of the algorithm itself, This is very, very good, as it turns out. Structurally, there's a few insights with Accord that make it novel, make it unique, and make it smart enough to basically, for multiple things that are in flight, figure out what collides, what doesn't, what is it safe to do, and what do I have to wait for to do. And I'm just gonna leave it at that kind of high-level hand-waving, woo. But the reality is, there's an immense amount of work that has gone into this. There's an immense amount of proof work in terms of a single-threaded simulator that confirms and makes sure that the order things are executing actually holds to and adheres to the different commitments and invariants of the algorithm itself from the proof that we're doing. And if you look historically at all the work that's gone into Cassandra in the past, a CEP with a mathematical proof of an algorithm is not exactly our status quo approach to the things that we do. So it's been really, really cool and really, really good to see how this has worked out and how it continues to evolve. So, with all that said, what do we take away from, for those of us that have hitched our wagon to Cassandra, or that love to contribute, or are thinking of building out things on top of it, or whatever your posture and your position and relationship may be? Users are moving around. They are gathering in different places. And we need to meet them where they are, wherever that may be. And I was joking a little earlier today how it's like in the ML space, it's like emojis everywhere. Like every README you look at is like a wall of emojis. And I'm like, well, I guess this is what they're doing now. Like, I'm good with it. Let's meet them where they are. So I don't expect Cassandra to be covered with emojis. Don't get me wrong. But again, like where are the users gathering? How do we connect with them where they are? How do we, in the space of enlightened self-interest, learn from that so we can better make our software serve their needs? We really should do that. Turns out working together is a good thing. Who would have thought? The models that we're using for collaboration on the project are actually being noticed outside of our project. So the Cassandra Catalyst program is something that a bunch of other projects are kind of looking at and trying to figure out, hey, this might actually be something we want to do. The way that we're working with sub-projects and governance is part of that broader discussion of other projects who have sub-projects, and they're saying, well, how do we do this? Well, here's the way the Cassandra team is doing it, and that seems like it's going pretty well. And it's great to have Mick on the project, who knows a lot of these folks and can kind of grease a lot of the skids behind the scenes to kind of talk through like what our thinking is and what we're doing. There's an immense amount of work with other projects that happens behind the scenes, so we can all kind of learn together and figure out, as the industry changes, as these different governance regimes and political regimes change, where do we fit in with that, and how do we make sure our project remains relevant? But yeah, collaboration works. Yeah, it turns out testing is useful. Testing is worth it. The shift towards property-based testing and fuzz-based testing has had a massive impact in our confidence with the system. And there's I think, definitely a lot more work to be done. There's a lot that we need to figure out in terms of the signal-to-noise ratio with what we currently have as our corpus of tests, because we don't want to like contribute to burning down the earth by running thousands of machines every time we validate one commit, which is kind of our current MO and my axe to grind. But yeah, we're actually in a really good spot. There's nothing I look at and say, I am deeply worried. Here's a thing we need to focus on. And I think we're doing all right. So that is what I have for you about the state of the dev community and the project. Does anybody have any questions? No questions. I'm hearing that I am too long-winded and we don't get questions. So thank you, everybody. Appreciate you coming out and appreciate everything you do.
fine, sir. You want to keep this one? Instead of my computer? Place it over here.
Hey, sir, do you still have the?
That should be up on the.
Okay, thanks. Just wanted to make sure while you're still here.
We do not have.
Is he plugged in?
Yeah, we. No, we do not have. You have the computer. How do you connect? You have a computer on? No. Can you pull it up? Can you see? But we need something.
You need a dongle?
Yeah.
Or do you?
I do not have.
You don't have. Can you mute those mics?
Oh no, actually.
Can you mute their mics?
We ready to go? Okay. Good afternoon, and thank you everyone for joining us here today. So we hear a lot of things about new applications being built and using Cassandra at scales and new technologies, but we do not normally hear about how do we migrate older applications, existing applications to newer technologies. So there are some applications which have been running for last 50 years. They are processing hundreds of millions of customers' profile data and billing data, and we are here to present a story about how we moved an application like that to the new technology. We went through the entire transformation. We took the application from on-premises and relational databases and moved it to cloud and into Cassandra. And this was an exciting opportunity for us at Verizon Wireless. So my colleague and I are going to tell you that story, and we are going to pinpoint certain interesting facts about that. So this is not going to be an in-depth presentation about how we set up Cassandra, how we configure Cassandra, but certain interesting facts about data modeling that we learned, and I hope you will be able to appreciate and enjoy it. My name is Sunil Dabre, and I've been working in Cassandra for past 7 years. And this is my colleague Chandi Datta. He has been the SME for everything Cassandra in Verizon. So before we start with how we did it, I just want to give you a little bit shout about Verizon. Everybody, I hope, knows about Verizon. I don't need to go through this, but this is something that's required from me. So what are we trying to address? What were our pain points, and why did we embark upon this journey? So I'm going to concentrate specifically on the database side of the story. So when we started this journey, Verizon had fragmented regional databases. Even though we are a national company, we had different databases which were independent. So North customers were in the North data center, East customers were in the East data center. So all the databases were fragmented. There was no single SOR. There was a very high cost of ownership because of proprietary licenses, and especially because we used to have all these fragmented databases, so there was no centralized way to manage all the databases. And of course, we had a performance and maintenance complexity because any release would need us to do the same things on all different data centers. So that just added to the performance and maintenance complexity. So what were our requirements? We wanted something that was, of course, cost efficient, low maintenance, because we were already looking at a high maintenance solution, and we wanted something that was simpler than that. Of course, we wanted something that was scalable because we want more and more customers, right? So we want something that's scalable, that can grow as we grow as a company. We wanted something that was cloud native and hybrid. So we did not want to stick to on-premises and have those costs. We wanted to make sure that whatever database we choose can also go with the modernization of our applications. At the same time, one of our major pain points was regional databases. So we definitely wanted something that had cross data center replication built in. We did not want to go ahead and have 3 whole regional databases in 3 data centers. We wanted something that could automatically replicate the data across all the data centers. And of course, performance is always a requirement, and availability. And most of you know what is the answer to all these questions. So I'm going to turn over to my colleague Chandi Datta. He will take you through the challenges and complexities, and he will take us through how we started our journey and where we are. Over to you, Chandi.
So, we started, as Sunil said, our requirement was it's not a greenfield applications. We started as existing applications, and we want to build on top of it. And at the same time, we want to migrate our applications. So if you take a look at our stack, it's like 1,000+ API, existing APIs were there. And top of that, it's a mainframe world. It's so many bad jobs are running. So how do we, there's a big task, how do we migrate those things in new stacks? So before I start, so our journey started long back, before even Verizon Wireless formed. So think about it when we are in monolithic mainframe stack where everything moved at its pretty much delivered space, where you want to access your data, you want to update your data, you have to go through complex loops. And top of that, all MIPS cost. So if you want to add an engine, then you have to go through whatever your vendor, and then you have to corresponding cost you have to bear. Now, we wanted to change, and then in-memory database emerged. So we thought, okay, in-memory database is going to be a good fit for our stack. But in-memory database came with its own bells and whistles. So and it's still, as Sunil said, it's end of the day, it's a fragmented database, and we want a national database. So it failed to meet our national database requirement. And then came Cassandra, and immediately it met our requirement through its out-of-the-box replication. And with that, it's our journey started with that. It's move on with Cassandra. So with that, let's move on to the next. So before we proceed to how we did it, as Sunil said, we'll tell you a story about why we did, how we did our migration. So as I said, our journey started back in 2000 when Verizon Wireless formed. It came or acquired assets based on Bell, AT&T, and everything. So everything came over from our sister company. So that time, everything born based on heads down mainframe, applications writing to mainframe, and application reading from mainframe. Now, what kind of data we are talking about? We're talking about system of record that contains profile data, billing data, order data. So these 3 are the key thing of any company or company like Verizon Wireless, where if anything goes wrong, we'll be in big trouble. So if we want to migrate our existing stack to a new stack, we had to make sure we are not touching any of the ecosystems. So we do not want to we don't want to change anything existing. So if anything we want to make sure if new stack, anything happens new stack, we always can fall back immediately, and that leeway is pretty low. Like 1 minute or 2 minutes, we can fall back. So less impact to our customer. So what we did, we started with our read journey first. So, we are writing to mainframe, and then we started replicating mainframe data to Cassandra in real time. So even though it's kind of small box, but it's a lot of things baked into in the real-time replications. And it's as you can see, the customer, suppose you are in VerizonWireless.com and you are adding a phone line, suppose, and immediately you want to see whether phone added or not, or the provisioned or not. So those things
getting data into mainframe and immediately served from Cassandra in real time. So it's like big round trip we had to make within certain milliseconds. So why we did that? Because one thing is, as I said, the MIPS cost in mainframe is like if you read more, you are going to pay more. So we want to get rid of our MIPS first, like as soon as possible, so that we can, like, we do not have to add engine in iconic time, any like Black Friday or any holiday periods. So we copied like our data in real time from mainframe to Cassandra, and on top of that, we added all our API. Even though we migrated data, as I said, we didn't change any of our existing API. So earlier API, if you think of in RDBMS world, is like 1,000 tables. It's interacting with 1,000 tables. But in Cassandra world, we had to mimic exact same thing. Or else, like, how do we can like replicate data? That was one of the biggest challenge that we had, because we are not changing any of our interface API side. Like once we are done with that, and then our final target landscape was get rid of mainframe and write directly to Cassandra. So before I move forward and tell like how many tables we had and data model, I'll just quickly touch upon this one and debunk the myth that like Cassandra data modeling is kind of an insurmountable challenge when it comes to brownfield applications. So before like a second one from the last probably, somebody said from Intuit, like if you're starting from Cassandra data modeling, please get a separate hand, because it's not easy thing. But what we felt it's easy thing to do once we understand how Cassandra unique way they are storing the data. Once we know that, it's pretty easy things. But even though it's easy thing, what we felt, it's like one data model today, it's may or may not going to work tomorrow. So how do we change or how do we adapt that one? So glimpse of our like high level or backend. So it's like we played by Cassandra rules. We followed Chebyshev diagram, we followed logical model, physical model, and one table to one query entity. We followed everything. So we had like, before denomination, we had like 800 plus tables, and we end up having like uneven size partitions and hotspots nodes. I'm sure like if you are familiar with Cassandra, you faced same thing, right? So we face the same thing. So with that, I'll hand it over to Sunil to start with our use case, like data model use case. How do we tame those things? Sunil.
Okay, so let's look at a very simple use case. Okay, so how did we reach this point? So for a particular telecom company, right? So two of our main entities are phones and customers. Customer has phone belongs to a customer. So two of our like simplest queries would be, hey, I need all the phone numbers for this particular customer, or if I know the MTN, I need the customer number. Let's say you call me customer service agent, he knows the MTN, he needs to know the customer profile, so you need to get the customer data. So these are our most simple use cases. You can't get simpler to this in telecom. In RDBMS world, only one table is sufficient. I can have a table, customer number, MTN, I can query by MTN, I can query by customer number. Obviously, that's thrown out of the window when it comes to Cassandra, right? So now how would the table definition look like in Cassandra? You have one table which says MTNs by customer, where you have the customer ID as the partition key and the MTN is a column. And the second table is customer by MTN, where you have MTN as the partition key and the customer ID is the column. Of course, there are a lot of other attributes, but I'm just leaving them out, right? So these are the traditional approaches that we use to arrive at these data models. So do you foresee any problems with these data models? Partition size. What else? Consistency, of course. Okay, let's see. What happens when a customer has millions of mobile phone numbers? Of course, we are very happy, the business is very happy. Okay, but what happens to the DBA? Okay, so the first problem you are going to hit is there's going to be too much data stored on the base of customer ID, right? That's going to be large partitions. And when we go in the IoT space, sometimes the customers have millions of phone numbers, right? Because each device has a phone number in the background. And of course, we can't efficiently read or process this data. At the end, Cassandra is just a JVM. It's handling requests, and if there's large partition that's much more than 100 MB, and if you keep on reading that, the JVM is going to be in trouble. Of course, then the next problem is consistency. This is a very simple use case where we have stored the same data 2 times, right? We might have other use cases where we end up replicating the data. How do we make sure that all of those are in sync? Because table by table, we can say local quorum, but if I have an application path and I'm writing into 2 different tables, how do I ensure that they are in sync? Because anything can fail. And the nodes are unbalanced, right? Not all customers have millions of data. And in the RDBMS, we can roll back. Of course, that's not possible in Cassandra. But we have adhered to all the data modeling rules. So what do we do here? So adhering to pure data modeling rules or whatever you see in the blogs is not the critical success factor for success, right? There are certain things that you need to do, that you need to look at your own use case and see how you can achieve what you want to achieve. Now let's look at this through the lens of the transformational project.
Okay, so thank you, Sunil. So the first problem that we are going to address is like the large customer, right? So, or large partition. So if you go through any blogs or anywhere, so everywhere, like, or even from your side, you already did it probably in your installation. Okay, so if you have a large customer, okay, or large partitions, let's partition it, even do micro partition, like add a synthetic column, bucket number. Okay, so we did it, but wait, as soon as you add that one, then we are creating another problem. So suppose earlier, like 1 query, you're retrieving 1,000 rows. Now you have to write like 10 queries to retrieve 1,000 rows. So you are, instead of like fixing one problem, you are creating one more problem. And that, because of that, you are creating a latency. So if you have like a latency sensitive applications where you need to serve your customer or serve your API within certain SLA, SLI, then like you cannot just randomly do partitions. So you have to be mindful. So how do you like tame these one? Okay, so before, like we all know, like Cassandra works if we distribute our data properly, like data density across nodes should be proper, not uneven. Now that's a pros thing if we added a bucket number. Now too many queries and read latency is going to be cons. Now how do we solve it? In our case, what we did, apart from adding bucket number, we added something called kind of T-search sizing. As Sunil said, we have IoT customers. Not all IoT customers are large. Or we have a business customer. Not all business customers are large. What we did, we added like a sizing, like some are small customer, large customer, and a mid-sized customer. And we categorize those ahead of the time. Now, you might be thinking, oh, well, you know certain customers, but what about new customers, all right? New customers you don't know, tomorrow they might become a large customer. How do we solve that? Okay, so we'll come back to that problem, but for now, how we did it, we went with T-search sizing kind of concept where, like, and our API side, like, we are aware where to look for. Like, if we are asking for customer ID 123, okay, so the API side, they are aware, oh, customer 123 is large, so I need to look for large bucket only. So now the question is, do we need to the bucket customers ahead of the time?
Well, not necessarily, right? So the process that we used is that we had certain thresholds, and when a customer moved beyond that bucket, we did something called rebucketing to move the customer to the next bucket, right? So sort of like there's always pros and cons, right? So by this approach, we are able to get rid of large partitions, and vast majority of our customers are small, right? So vast majority have like 2 MTNs, 3 MTNs, right? So for the vast majority, there is no impact, but for the other customers where we bucket into 10 buckets or 15 buckets, like we do the extra queries, But the beauty of Cassandra and the Cassandra Java driver is that we execute all those queries in parallel. So there's not going to be that much of a latency impact. So as long as we can scale out, and instead of like getting all the data from one node, through bucketing we go to different nodes, we are able to achieve what we want. So the next big problem that we had is that since it was a brownfield application and we did the read first, we had to get the writes into Cassandra first, right? So the writes were happening into DB2, and we were doing a real-time sync from DB2 to get data into Cassandra. So this created like a couple of constraints for us. Since the way we were doing the data migration from DB2 into Cassandra was not based on API or functionality, but it was based on tables. So whenever something changed in a DB2 table, we put a message in a queue, and then we process from that queue and write it into Cassandra. The problem with that approach is that we are sort of strictly tied to the model. So whatever model we had in DB2, we had to follow similar model in Cassandra because the data comes table by table. So this was one of the things that we had to do. The only way we could get the read first done, because the read first was our entire strategy to make sure that we achieve what we want in terms of like cost reduction and to even prove the stability of this product. So one of the key things that we utilize while doing the read first strategy was utilizing something called the Cassandra concept of using timestamp, right? So everything that you write into Cassandra has a unique timestamp. So if you write something with a timestamp, and after that you come and write something else with an older timestamp, then that's effectively shadowed, right? So everything that happened in DB2 has some timestamp. So if there's an insert, then it has a timestamp. If there's an update, that has a timestamp. So even if we got the two messages out of order, the update came first and the insert came later, still, because we were storing the data with the using timestamp, we were still able to make sure that the data in Cassandra was functionally correct. So this was one more challenge we had to go through, and this typically you would not hear somebody using that using timestamp in such a way.
Okay. So one more challenge that we faced is like a inconsistency issue, right? So as we said, like one table in our DBMS, it's corresponding to maybe many tables in Cassandra world, because the way our API, exactly we had to serve our API. We are not changing our API queries or anything because we had to fall back. So when we did that, so same table in suppose customer by MTN, we had to have like multiple renditions. So one by MTN by customers and another customers by MTN. Now question what we faced is like sometimes like, hey, data are not in sync. Okay, sometimes we are sending like like wrong data. So one customer is like 5 MTN and another customer same time from another API we are seeing 4 MTNs. So the question is like, how do we trust our Cassandra data? So we had to come up with the reconciliation process. So reconciliation process was a Spark-based reconciliations on the fly. It's going to calculate like back of our systems like daily recon or weekly recon, monthly recon, the large tables, or like where we have like like heavy transactions that are coming, those tables like daily recon or hourly recon, and making sure the data, actual data is coming from source to destinations are in sync before even customer notice it. If customer notice it, they might get a ticket, but before even we go there, the reconciliation process that we use that helped us. And another thing that we all know, Tombstone. Okay, this is our favorite thing in Cassandra, right? Like sometimes I tell my son, is like sometimes he said, is like, hey, what is Tombstone? So I was like, Dad, you are working on Tombstone? And no, I mean that's a separate thing. So Tombstone is kind of we all know it's helped the data consistency issue with Cassandra, eventual consistency. I'll not talk about that, but we all know that now. And also we know Tombstone can and like create issue with our read problem and stuff. Now what, like I'll tell you what we did. Like suppose if think about it, like we place an order, customer places an order, and immediately the order goes to something called pending table, and then that tables become hot. We have all our main data storing over there before it's basically fulfilled. Customer, like we have to fulfill those orders. And then once it's fulfilled, it goes to completed order tables. Now, earlier, the pending to order table is based on customer. One customer placed, suppose, 1,000 orders. So we are placing over there. And then once it's done, we are deleting those rows and we are inserting in the completed row, cold data. Now, while did that, next subsequent call, we are hitting those tombstones. And that was causing lots of issues. So what we did, in our side is like we created a secondary table called lookup table. Over there, we created like customer and order relationship. So we are just storing that relationship over there, and our main pending table is only store order data. That is like only one key, and the order informations are stored. And that way, we are uniquely identify the order, and then once it's fulfilled, we are moving that order to our completed tables. So that way, we are, even though we are creating tombstones, but our API is not reading tombstones. So that way, we are able to alleviate our tombstone problem. And we had like another problem is like too many tables. So if you go to data stack side or anywhere, like clearly say, hey, don't go more than 400 tables. Okay. So but we had like more than 1,000 tables. Okay. So 1,000 tables. So think about it like running repairs and all other things. And on top of that is like our transaction volume like 1.7 million read transaction per second. And with like more than like 300K writes per second, we had to go with like 800 tables. So like it can create heap pressures and stuff. So how do we even get there? Like, so you can go ahead.
But this is what our modeling led us to, right? Because in typical Cassandra, you always hear that you need to have a table per use case. Now we have thousands of APIs, we have thousands of use cases, like in the same data. So we end up having that many tables, right? So a couple of things that we tried to mitigate for multiple tables. So we tried two approaches. The first approach was to combine multiple tables into one, was sort of a column-based approach where we took the 3 tables and laid out their columns in a row, right? So you are combining vertically. The problem with that is that when we try to do that, because of the nature where we are getting data out of sync, let's say we are trying to combine 3 tables into one row, sometimes we might not have the necessary keys to combine those tables, right? So the approach we went with to combine is to combine the rows horizontally, so that we created reference tables where we had synthetic keys saying the table name, this is the table name, and then these are the values, and that's how we sort of combine the tables. I know we are running out of time. Okay. So one more important question that I want to ask, right? Can we ever model for all the questions that we want to ask, right? A business like ours, right, and business users want a lot of information, right? Orders, MTNs, customers, this is just tip of the iceberg. We have thousands of plans have thousands of variations. They want to slice and dice with all those variations. Can we ever model for all those questions in Cassandra? Maybe with version 5, where they are promising indexes, but definitely not with secondary indexes, definitely not with materialized views. We could not resolve this. So what we did, we created a CDC pipeline to take the data from Cassandra and put into RDBMS, and all our ETL and business related ad hoc functionality is served from there. So that's where we are at this current time. So what are the lessons learned? We did all the mistakes that we could do, okay? And our business is a business that runs at scale, so our APIs require millisecond latency. If there's a customer, and we all know how customers work, if they click something, they want a response back within a second, right? And if you cannot achieve that, they are going to move away. So what are the lessons learned? So Chandi is going to go over that.
Okay, all right, so thank you, Sunil. So the first thing that I'm going to, let's take a pause and reflect what we learned so far. We talked about our unique challenges that we faced, and also we talked about a bit on how do we mitigate those challenges. So apart from that, the few things that I want to talk to you is Cassandra in general, it's pretty rock solid. So it worked for us, like out of the box replication, then scaling, it's solid. Okay, so once you throw it in, like it's done. You do not have to do anything. But as soon as you start using the features, or from our side, what we felt, as soon as start using like all the other bells and whistles, like secondary index, materialized view, triggers, then even like SASE. Okay, so we felt it's like, since most of our background is RDBMS based, we felt like, okay, let's go ahead and use it. But it didn't work for us. It scaled up to some extent, but in 10x, 12x, it never scaled. So after that, it was like we stopped those things. Like, hey, we're not going to use any of those features. So including collection data type. So we faced many issues with collection data types. So I saw like left and right folks use collection data types when we started our journey. Then from there onwards, we kind of moved away from collection data types because it gets a lot of tombstones. And so one thing that we learned, it's something we want to learn, and we have to unlearn something else as well, because our prior, like what we felt, like prior knowledge sometimes create hindrance to move towards new system, because we're coming from our DBS background, and folks like our leadership or whoever is seeing the blogs, they are just seeing the high level, and they're saying, hey, as an enterprise, what we felt like more and more, we want everything from Cassandra. But that's not the case. So like even though like in like earlier talk, Josh wanted to say ACID transactions are coming into Cassandra. So that can be, or even vector search is coming into Cassandra. But even though in future, it may or may not the scale that like company like us we are looking for. So with that, I will finish our session and we'll open up for questions.
Thank you.
Thank you. Okay. If you guys have any questions, we can answer.
If not, thank you.
Thank you.
Go forth and unleash the power of Cassandra.
Go ahead.
Mm-hmm. Cassandra compaction for the tombstone issues you had. Did you consider those solutions?
So
okay. So we just like concentrated on little bit issues concerning data model, right? Of course, compaction is a regular issue that keeps people awake at night.
So yeah, so compaction is like in Cassandra, it's we tuned, like even we have tuned in such an extent, like at the table level, also we have compaction. And some cases, like even we create a separate cluster for those set of tables so that we can run our regular repair, and also like the table where it's required like frequent writes, those tables we moved somewhere else. So that way we cannot, what I'm trying to say is like we cannot fix the compaction issue is there as part of Cassandra. It's not an issue, it's a feature. So and it's there for a reason. It's going to chew your resource. So some cases like suppose size-tiered compaction strategy if you're using. So we are making sure we're mindful, like we're not storing huge amount of data. If you're using level-tiered compactions, we are mindful it's not going beyond certain number of SS tables, because we might say like level DB can go beyond something, but actually if we are going to scale, we have a background job that is going to periodically is going to tell us, hey, it's going like breaching our threshold, breaching your threshold. So either tune it or move your data somewhere else. Okay. Okay.
So how do you solve the API questions? Like there's 1,000 APIs, right? Since you the Cassandra recommendation is to design the table based on your query. So what happened to that?
So that's a very good question. So we touched upon that one. So what we did is, remember what Sunil said, is some of our, like out of 1,000 API, not all APIs are transactions. Some APIs are looking for reference data. So we categorize those API and we find whatever tables they are touching, we merge those tables and create a one table. So that way, suppose we like at least close to 700 tables, that reference table in RDBMS, we merge into one table. So that way, it's like still 1:1, but in Cassandra, it's one table. So that is like a reference table. And also we have the way, we structured such a way, like we have a key to know where it's storing. It's kind of metadata also. We have another table so that API can look for the data from that particular table via the metadata. And all other tables, we have many tables. We still like deal with like many tables. So at this point, like we are, as per data stacks, we are the crazy customer that like we have 800, 900 plus tables. So we are still, even though we merge certain tables, but still we have like more than 800 plus tables.
So I think in general, right? In general, they say that like one API, one query, right? We are not able to reach that, okay? And if we try to do that kind of thing, we are going to go into all types of data replication issues. So typically, the pattern that we use is like creating some search tables. Instead of duplicating all the data, just create some identifiers in some search tables, and then get those identifiers first, then get the data, right? So even though we have multiple APIs, and typically with this pattern, you add a few queries. Definitely, you add a few queries. Your API is not going to be like one query or two queries. Instead of one query or two query, it might be 4 or 5 queries, and some queries are dependent on each other. But that is the reality. It's not possible to always model to one query.
All right. So if you have further questions, I'll try to answer your questions after this one.
Thank you for your time.
Thank you, folks. Would you water?
Good job. Done.
Thank you. Yeah.
Okay. Your water? Your water? I'm water.
Hello, everyone. My name is Piotr Kołaszkowski, and I got a talk on storage-attached indexes that are coming into Cassandra 5.0. I hope that the feature that I present will solve at least some of those problems that were described just in the talk before from Verizon about data modeling. So, yeah, when I started my experience with Cassandra, I remember that I did some trainings. I gave some trainings to people who were mostly aware of relational databases, but Cassandra was new to them in those days. Well, I'm talking about, well, times 10 years ago when I just was starting working for DataStax. And I showed them CQL language. They were very excited because the syntax is kind of familiar. Like, it's almost like SQL, right? I mean, you got create table, you got select, update, delete. I mean, they said, like, why do this training? We already know this, right? And then we started doing some exercises, and they quickly created something similar to this. Maybe the example was slightly different, but, well, simple table with a few columns. And then they tried to do this select. Here we got a column which is color. It's not a primary key. And it turns out that when they try this, they got this. And what is that? Yeah, it took me a while to explain what allow filtering is. But this talk is, of course, not about allow filtering and how it works, but mostly how to avoid this. So, yeah, in order to fix this problem, Cassandra originally offers a few solutions already. Like, one solution is, of course, to do what is suggested by this error message. The error message tells you, OK, use allow filtering. Yeah, you can do this, but it is useful only in a very small subset of use cases. If you're filtering low amounts of data, that would be probably fine. The problem with filtering is that the filtering happens on the server side, or both on the coordinator and the replica level. But if there are many, many rows to filter out, you might, well, traverse thousands of rows before you even hit one live row that you need to return to the client. In this case, it's very likely that you run into timeout issues. And even if not timeouts, then the queries would be simply slow and consume a lot of resources. This won't work very well. Another idea, which was already presented also in the previous talk from Verizon, you can denormalize by hand, so like create separate tables. Each table stores the same data, but in different order. And then you can direct your queries to proper tables that are laid out in such a way that you always query by the primary key. And in this case, it is fast, but it also has some operational problems, like, well, consistency. You're also duplicating a lot of data, so actually you need to prepare space for the data. There is a feature called materialized views that is supposed to automate some of that, but current implementation also runs into some consistency and operational issues, so it might work for you, but not always. And then there is a bunch of indexing options in Cassandra. There are legacy Cassandra 2i indexes, secondary indexes, which are unfortunately working in a very similar way, like creating a separate table locally on each node. So they also have some problems. They're pretty limited in features. Like, for example, as I remember, there are no range scans, and you cannot use multiple indexes in the same query on multiple columns. Then there is SASE, which is a bit more modern, still a bit experimental, and also has its limitation that you cannot put multiple indexed columns in the same expression on a single query. And now, the feature that I'm presenting, so SAI, storage attached indexing. This is a big improvement over previous indexes. It doesn't solve all of the problems, probably, but I guess that it should be good enough. OK, the basic syntax is very simple. create index. You just need to specify using SAI to tell the database that you want to use this kind of index. And there is an option, like in the Cassandra YAM, you can set default secondary index enabled true. In that case, your statement could be simply create index, and it would automatically choose SAI. Okay, so let's see this example again, like with indexes. Of course, it works. It returns all yellow fruit. Returning yellow fruit is a very important problem. Like for anyone who has kids, probably knows that they have various preferences, not just on the taste of the food, but also the color. For example, my youngest son won't touch anything that is red. Doesn't matter if it's tasty or not. Red can't do. So yeah, this way we can just get all the yellow fruit. But what about if we wanted, well, lemon is probably not a good thing here. I mean, my son would say, okay, I like yellow, but lemons are yellow, but I don't like lemons. So please give me meal without lemons. So we need to add another condition. So for example, bananas are okay. In this case, this works with SAI. So you can use multiple indexed columns. The system would intersect two indexes, and it will return proper result. We also get range queries. Range queries currently work on numeric data types. There is a plan to support them on all data types in the future. And of course, you can mix range queries together with just equality queries as well. So as in the previous example, I mean, this all composes pretty well. Those queries are also pretty fast. Like, I mean, it goes directly to the index, fetches just some sub-branch of the tree, and yeah, I'll show later how it's executed. But there is no filtering. That's the most important part of it. Collections. SAI also works for collections. So we know that Cassandra supports lists, maps, sets. So that's a bit more complex because, for example, maps have both values and keys. So you can create, for lists and sets, it is easy. You just create an index on the column as usual, and then you can ask, like, please give me rows where the collection contains given value. For maps, it's a bit more complex because you have this additional syntax. You can tell it, like, which part of the map you want to index. Is it keys, values, or more maybe both, keys and values? And if you create proper index on the map, then you can also ask queries like, for example, give me entries which contain given key or which contain given value, or where there is a specific value associated with a specific key. So in this case, actually, the index would be constructed on both keys and values, on key-value pairs, and it would be used to search for given pair, and if it finds in the index, then it will return the row. Yeah, here's the example. So we have a bunch of maps, and then we create an index on keys of those ingredients maps. And as you can see, the query with contains key cheese returns just the items with cheese. Okay, let's look at how it's implemented. So generally, a secondary index is a data structure that allows you to associate some indexed term with a list of rows. Actually, it's a list of pointers to the rows. So like the index is not really duplicating the row data. It's just storing the identifiers, row identifiers. And of course, with a single indexed term, with a single value, there can be more than one row associated. So like in this map example, let's go back. You can see that for cheese, like we have two items, two rows. So in the index, we have one term cheese and posting list. The posting list is a list of row IDs. So we got 2 rows associated with that. That is, of course, a very, very simplified view. It's just a high-level overview. In reality, the data structures that we use are a bit more complex. So how we do that in the physically in the database. Each SS table and each mem table has an associated index. That index is just the data that were inserted into that SS table or mem table. So those are not global indexes. Those are local to SS tables or local to mem tables. This makes it very easy for us to keep the data consistent, because indexes have the same life cycle as SS tables. So whenever Cassandra flashes a new SS table, we build an index for it. And it's immutable, like the SS table itself. When the SS table gets compacted, eventually it gets deleted. The index gets deleted as well. And of course, we get the index data already in the new compacted SS table. So this is very easy to get consistency. Each index, and this is something unique to SAI. SASE didn't have this. Each index is actually a set of files. It's not a one file. And we got 2 types of files, 2 types of components of the index. One type of component is per SS table files. So we realized that some data that we want to index are actually common for all the indexes on this particular SS table. So like if you want to create 3 indexes on 3 columns of SS table, some data actually would be common. I mean, data like primary keys, we need to store them only once. So there is no point in repeating that data and duplicating that data in each column index. We store it once, and all the column indexes use that data. So this is what we call per SS table index files. And of course, each indexed column also has some components. Well, that is typically the tree structure or tree-based structure that allows us to quickly map between index term and row ID. When we're writing data to an indexed table, the data goes as usual to mem table and commit log. And for mem table, we also have mem table index. So when the mem table fills up and there's time to flash, the mem table gets flashed into SS table, and the mem table index is also literally copied to a SS table index component. This process is fairly straightforward and quite efficient. Of course, the whole flash happens asynchronously, similar to like just traditional way how Cassandra does flashes. Okay, eventually the SS tables need to be compacted. And here there are 2 ways that we could achieve the same effect. Currently, what we are doing is, like, after the SS tables get compacted, the compaction creates, writes new rows to an output SS table. We register a listener on those rows, and we feed those rows to the index builder, and this index builder basically builds a fresh index from those rows. We are not compacting the indexes. That is an alternative solution that we are investigating, that we believe that in future would be faster to actually take just the indexes and compact them together instead of building a fresh index from SS table data. Currently, you might notice some slowdown because of that indexing building on compaction. So we don't recommend creating too many indexes per table. Like 10 is okay, but don't go don't go too far beyond that, because yeah, it might slow down compaction a bit. This is of course the index building is done synchronously because we need to have fully operational index before the SS table is marked as usable in the system. Read path. Well, for read path, because each index is local to mem table and SS tables, we have to, of course, consult all of them. So first, the query goes to each index. It returns an iterator over primary keys. Again, a simplification. This is a multi-stage process to get a list of primary keys. So we get a primary keys. One nice thing about this model that Cassandra uses is that all SS tables are actually sorted. They're sorted in the same way. They're sorted by token and clustering. So because they are sorted, it's very easy to merge them. And then after we are merging them, we get a list of, well, all primary keys on that node. And then we just go to the storage and fetch data, fetch rows by the primary keys. This version of SAI that goes into Apache Cassandra, so as a part of CP7, is row aware. So it actually indexes exactly rows, not partitions. We had earlier, we had an internal version of SAI that actually indexed just partitions. It was a bit easier because we didn't have to store primary keys, we just needed to store tokens. So in some use cases, it was a bit faster, but well, if you had wide partitions, it was not good because it had to filter all the data of a partition. Here, this is much more precise, and this is going into Apache Cassandra. Well, one more thing, there's post-filter block. So after retrieving the rows, we still need to filter out, so like recheck if the row matches the selection criteria, because indexes do not track deletions. So like if you have tombstones, so yeah, tombstones of course track deletions, but this is for Cassandra for like primary keys. And here, because we don't record deletions, we might hit some false positives. That's why we are post-filtering them to return correct results. Okay, what if we have query involving multiple columns? So like here we have column name, column quantity. Then we just open an iterator on one index for name, open iterator on quantity. After merging, then we have another block that's intersecting two iterators. So basically it returns only the primary keys that were present in both of the iterators. Again, because the order is the same, it's easy to do this operation. However, there are some costs involved. So imagine that those indexes on both sides return just a very tiny subset of rows. You get 1 million rows, for example, but each return just 10 rows. So whenever you get one item from the left index here, you have to find if there is a matching entry on the right one, on the right iterator. So we have internally some kind of skipping operation. It's actually called skip2. So we instead of just fetching all the things from both iterators and comparing naively, we just ask the second index like, hey, can you move forward to the point with this primary key? If this primary key is not found, of course, give me the next available ones. And this operation is a bit costly, but again, it's still often faster than just going through all the entries. Because like if one index was very, very selective and another one was not very selective, like one index, for example, was something like a Boolean flag, you can index Boolean here, right? True or false, 50% might match. Right? So if you had that, then you would probably not, another index that is very selective wouldn't be any good because you would still have to go through all the entries on the other side. So that's why we have the skip operation, which in this case skips forward by many items much faster without going through the data file. But of course, beware that if you put multiple columns in a query, those intersections, they do cost a bit more performance. So it's not as fast as selecting from one column. And yeah, detailed stuff. So like I said that the index returns a list of primary keys. That's not exactly like it is done. So this process has multiple stages. So first we have actually two types of indexes. So we have trie-based index. This is for string data, so for literal data. This is because tries have this nice property of compressing prefixes very well. So like if you have a lot of text, then all the prefixes will be actually stored once in the trie. This is the same data structure as Cassandra is using for mem tables, what was already presented by Branimir earlier today. For numeric indexes, we use some kind of KD tree. This is not exactly KD tree. It's a KD tree with one dimension, this block balanced tree, but the structure is very similar. So it's basically a tree with some blocks on the leaves, and each block packs some 1,024 items probably, if I'm not mistaken. But this is just a detail. So we get just row IDs from those either trie or the KD tree. Row ID is just a sequential number of the row in the table. Because as a table is immutable, we can just count rows from 0. This was designed like that because also those numbers are very small, so they compress very well. Like we don't need to store very big numbers. Like if we stored full primary keys in the trie, that would take up much more space, and that would be also much slower to search for. So we store just row IDs, and then we use a per SS table component, which is only once. It's a common component for all the column indexes on the SS table. Then we do the translation from row IDs to actual primary keys. So we have several maps, like row ID to token map, row ID to partition key, and row ID to clustering key. We have separate maps because often we don't need to actually map row ID to a full primary key. Sometimes it's enough to just map it to the token, because when we are doing comparisons, we can first compare by token. If the token don't match, there's no point in fetching the partition keys or clustering keys, because that's also a costly operation. So that's why those structures got separated. Then when we have the primary key, then we of course can go to storage and fetch the data. Okay, why SAI also improves over SASI and previous indexing technology? So we actually did a lot of, we use a lot of data compression techniques in how we design the indexes. So using row IDs is one example. Using per SS table component is another example, like not repeating the data, so avoiding redundancy at all costs. But also we try to be very smart in like data encoding. So for example, instead of like remembering when in posting list, instead of remembering all the row IDs, we can like if the table is small, for example, we don't need to use long integers for them. Like those integers are smaller, so we can actually bit pack them. If they're bigger, well, that's still not a problem. We can do something like delta encoding. So deltas between the rows are actually much smaller numbers than the absolute values themselves. So this way we can actually store much smaller integers and then use bit-packed encoding. So all those things together, they play very well, they amplify. So like using just a single technique maybe won't win a lot, but altogether, yeah, it works very well. A block-packed frame of reference, so actually storing data in blocks, and each block has something like a base number, for example, like a value that other stuff is just delta encoded from that. And also all the things within the block, for example, are using just 5 bits per integer. And we just store the number 5 bits is stored just once per block in the metadata segment. So those things result in much better disk usage overall. So here's a comparison with 10 column indexes on the same SS table, on the same table, sorry. And we can see that, well, there's the difference in disk usage is massive. This also translates to performance increase, because the less data you have to fetch from disk, of course, the faster it is. As for throughput, of course, it's very dependent on the type of query. As I said, like if you do a lot of intersections, it will be slower. I mean, you can't expect the same level of performance as you get from primary key lookups in Cassandra. That's really hard to beat. Cassandra is so fast that not many databases actually, can compete with it. So here, the performance would be, of course, slower than primary key lookups, but it's still much faster than filtering. For simple reads, like read unique, this is the benchmark which just reads one row from using just one column. We can see that it's still in tens of thousands per second. This is on a single node, but this benchmark is just a single node benchmark. When you do the ranges, it's in thousands, but if you do like intersections, which we have like different types of cardinalities, like low cardinality columns, high cardinality columns, we get a lot of different variants of those benchmarks. You can see that, of course, the performance is slower, but it's still in hundreds per second. So overall, if you look at latency, you can still most of the time be below like, 20 milliseconds and often below 10 milliseconds, which is fairly good enough. Okay, so the last slide, what could come next? There is work quite advanced on adding not operators, so negative queries, not in, not contains key, not equals. That's currently in review mostly. There are just minor fixes required. Then, well, indexing frozen collections, range queries on map values, so general range queries on other data types is what I said in the beginning, that we actually want to just remove the limitations. We know that there are some gaps still, so that might come in the future. Maybe also adding OR operator, like if we have both not and OR and AND, I could use, well, arbitrary nested expressions. This looks already like an RDBMS, doesn't it? Another thing, that's one missing point from SASE. Actually, SASE does that. So SASE has like support. SAI currently doesn't. But this is also like an idea that we might want to investigate in the future, doing full text search, maybe prefix search or suffix search. Okay, thank you.
Like string columns, literal columns, that means text?
Yeah, literal text columns, text, yeah, exactly. Okay, thank you. And if you want to collaborate on this, I mean, this is all open source, right? So there's ASF channel, Cassandra Sci, and there's also documentation already out there, so you can see actually the preview. Thank you. I take any questions if there's a little bit, a minute. Okay, so the question is about how extensively we tested performance of this on what kind of workloads. So, okay, yeah, we have a set of synthetic tests for SAI. So those are basically, this slide what I showed, this is a subset of those tests. There are many more. So actually loading 1 billion of rows yeah, 1 billion of rows, exactly. And loading that into a cluster and measuring latencies, measuring throughputs. We have this Fallout system. By the way, Fallout is also open source, so this is a distributed performance testing system that we use. Those benchmarks are run pretty regularly. And then, yeah, that's basically it. We haven't tested it on production workloads yet, but maybe that would come. I mean, we have some ways to do this as well.
What kind of stress testing tool did you use? NoSQL Bench?
Yeah, NoSQL Bench. So actually, yeah. So officially, we use NoSQL Bench, and NoSQL Bench is actually those results are from NoSQL Bench. I personally, because I'm also part of that team, so I personally also use Lata, which is my tool for just doing some stuff. And actually, this matched NoSQL Bench very well. So like confirmation from 2 different tools.
Was there any impact on heap memory for the indexes? A lot of it's disk. Did you
Yes, so there is some impact on memory and on heap, and like if you really index a lot of rows, there are some data structures in the indexes that are in memory, also they are loaded in memory. So they are used for accelerating access, so you don't have to touch disk every time. So yeah, adding a bit more memory for SAI is recommended. But this should be just a fraction of memory needed generally for mem tables. So I don't have any ballpark number at the moment, but I mean I guess like 10% probably should be enough.
Not 1,000%.
Sorry.
It's less than 1,000%.
Yeah. Okay, one more.
So I was just testing this SI index on the Cassandra 5.0.
Yeah, that's right.
So I was using for the vector search, and I saw there's a limitation for the number of rows it returns in case of vectors.
Yeah, but vector search and indexing is a bit a different thing. Like we of course use SAI in vector search, but there are still some areas that need to be solved, and we are currently working on this. So that's why we try to be conservative and like just don't let people run into problematic areas. Okay, we ran out of time, so thank you again for coming.